What mysteries lie outside the observable universe? Our observable universe spans 93 billion light-years, yet it's likely just a fraction of what exists. From multiverse theories to potential variations in physical laws, we'll investigate cutting-edge ideas that challenge our understanding of reality. Join us as we push the boundaries of cosmic knowledge and contemplate what might exist beyond our cosmic horizon. The observable universe is defined as the portion of the universe that we can see or detect from Earth, extending out to the farthest distances that light has traveled since the beginning of the cosmos. Due to the finite speed of light, which travels at 300,000 kilometers per second, we can only observe regions of space from which light has had enough time to reach us since the Big Bang. Currently, this distance is about 13.8 billion light-years, meaning we can detect objects that are up to 13.8 billion years old. This limitation is not merely a matter of distance, it is fundamentally tied to the nature of space and time. As the universe has expanded since the Big Bang, the maximum distance we can observe grows. However, because of the rate of that expansion, regions of space are moving away from us faster than the speed of light. Therefore, there will always be parts of the universe beyond our reach, where light has not yet had the chance to arrive, a phenomenon known as the cosmological horizon. The observable universe itself is only a slice of what exists. Beyond this horizon lies a vast expanse of space filled with galaxies, stars, and other cosmic phenomena that we are completely blind to. These regions are theoretically part of the universe, but remain inaccessible due to the limitations imposed by cosmic expansion. Understanding the observable universe helps bridge the gap between what we know and what lies beyond our current comprehension. The limitations remind us that there is still so much we have yet to explore, expanding the boundaries of our cosmic knowledge and igniting curiosity about what exists in the regions that our instruments can never reach. Our understanding of the observable universe has evolved dramatically over the centuries, reflecting advancements in technology, mathematics, and scientific theory. In ancient times, humans viewed the cosmos through a geocentric lens, believing the Earth was the center of all celestial movements. Observations were limited to the naked eye, making the universe appear as a fixed expanse of stars. However, this perspective shifted with the work of astronomers such as Nicholas Copernicus, who proposed a heliocentric model, placing the Sun at the center and ultimately expanding our view of our place within the cosmos. The invention of the telescope in the 17th century marked a pivotal moment in astronomical observation. Galileo Galilei's use of this new technology revealed craters on the Moon, moons orbiting Jupiter, and the phases of Venus, demolishing the notion of a perfect and unchanging heavens. As telescopes improved, so did our ability to identify distant galaxies, leading to Edwin Hubble's groundbreaking discovery in the early 20th century that the universe is expanding. This revelation transformed our understanding of the cosmos, establishing a deeper appreciation of its vastness and the relationship between celestial bodies. In contemporary times, technological advancements have allowed us to peer further into the universe than ever before. Satellites like the Hubble Space Telescope and missions such as the Cosmic Background Explorer have provided insights into the cosmic microwave background radiation, which is essential for understanding the early universe. Through these observations, scientists have developed the Big Bang theory, shaping our perception of cosmic evolution from an initially hot and dense state to the expansive and cooler universe we observe today. This evolving understanding highlights not only the dynamic nature of scientific inquiry, but also the impact of new discoveries on our comprehension of the universe. Each advancement in our observational capabilities continues to challenge and refine existing theories, reminding us that the observable universe is more intricate than previously imagined and inspiring further exploration of the cosmos that lies beyond our current limitations. Current estimates place the size of the observable universe at approximately 93 billion light-years in diameter. This measurement accounts for the vast distances light has traveled since the Big Bang, which occurred around 13.8 billion years ago. However, due to the ongoing expansion of the universe, Regions that emitted light allowing us to observe them are now much farther away than their original distance when the light was first released. The observable universe is not a static boundary. As the universe expands, our ability to see further into space increases, albeit limited by the speed of light. This means that what we can currently observe is only a fraction of the entire universe. As new astronomical instruments and technologies are developed, our understanding of distances in the cosmos improves, allowing astronomers to refine these estimates. Interestingly, the observable universe represents just a small portion of the entirety of the universe, which may be vastly larger or infinite. Some theories suggest that beyond what we can see, there could be other regions of space that are so far away that light from those areas has not yet reached us, hinting at a cosmos filled with uncharted territories. These estimates continue to evolve as we gain a deeper understanding of cosmic expansion and improve our observational techniques. Each insight adds layers to our knowledge and inspires curiosity about what lies beyond the limits of our observable universe. Measuring distances in the observable universe is a complex endeavor that employs various techniques and methods, each tailored to different scales of cosmic distances. For nearby objects, astronomers often utilize a method called parallax, which involves observing the apparent shift of a star against the background of more distant stars as Earth orbits the Sun. By measuring this shift, scientists can calculate the distance to the star using simple geometry. This technique is most effective for stars within a few hundred light-years from Earth. As distances increase, astronomers turn to standard candles, which are objects with known luminosity, such as certain types of supernovae or variable stars called Cepheid variables. By comparing the observed brightness of these objects to their intrinsic brightness, astronomers can determine how far away they are. Supernovae, in particular, serve as powerful tools because they can be observed across vast distances, allowing for measurements in billions of light-years. For even greater distances, scientists use the redshift of light, which is a phenomenon that occurs when an object moves away from us, causing the wavelengths of light to stretch. The more distant an object, the faster it appears to be moving away due to the expansion of the universe. By analyzing the extent of the redshift, astronomers can estimate distances based on the relationship between redshift and distance, which is governed by Hubble's law. This method has proven crucial for mapping the large-scale structure of the universe and understanding its expansion. Combining these techniques provides a comprehensive framework for measuring distances across the cosmos. With ongoing advancements in technology and observational capabilities, our ability to accurately gauge these vast spans continues to improve, helping to refine our understanding of the universe and our place within it. Each new discovery allows us to map the cosmos in greater detail, revealing the intricacies of its vastness. The most distant objects we have observed in the universe are galaxies and gamma-ray bursts, with some of them originating when the universe was just a fraction of its current age, roughly 400 million years post-Big Bang. One of the farthest known galaxies is GNZ 11, which was observed at a redshift of about 11.1, corresponding to a distance of approximately 13.4 billion light-years from Earth. This galaxy provides crucial insights into the conditions of the early universe, allowing astronomers to study how galaxies formed and evolved in those formative years. Another remarkable category includes gamma-ray bursts, which are extremely energetic explosions that can outshine entire galaxies. The most distant gamma-ray burst detected is GRB 2012-120A, observed at a redshift of around 15.2. This burst occurred when the universe was only about 500 million years old, providing an exceptional opportunity for scientists to study phenomena from an era when the first stars and galaxies were beginning to form. In addition, the Hubble Space Telescope and other observational instruments have detected ancient massive galaxy clusters like MAX J 1149, 5 plus 2220, further extending our view into the past. These clusters not only help astronomers study the early universe, but also contribute to our understanding of cosmic evolution and the distribution of dark matter. These observations highlight the extraordinary capabilities of modern telescopes and advancements in technology. Each discovery of increasingly distant objects allows researchers to piece together the timeline of the universe, offering valuable data on its formation and the processes that shape the cosmos we observe today. Beyond the cosmic horizon of our observable universe lies a vast expanse that remains largely a mystery. This region consists of areas of space that are too distant for light from them to have reached us since the beginning of the universe. While this limits our observational capacity, many scientists speculate about what might exist in these unseen regions. It is entirely possible that beyond our observable universe, there are galaxies, stars, and cosmic structures similar to those we see, but we cannot yet gather any direct evidence of their existence. Theoretical models suggest that the universe may extend infinitely beyond what we can observe. If this is the case, regions of space could be filled with celestial phenomena that mirror the structures contained within the observable universe. This implies that countless galaxies, each housing billions of stars and potentially even more planets, could be existing without our knowledge. This notion fuels curiosity about the fundamental nature of the cosmos and whether there could be other life forms elsewhere in this potentially infinite expanse. Additionally, some theories consider the possibility of a multiverse, where our universe is just one of many that exist independently. Each universe could have different physical laws, constants, and structures. While this concept is still speculative and remains a topic of debate among physicists, it opens up fascinating questions about the nature of reality and our existence within the cosmos. The regions beyond our cosmic horizon remind us of the limits of our understanding and the vast unknowns that lie at the forefront of cosmic exploration. With each advancement in technology and methodology, our desire to explore and understand these uncharted territories in the cosmos continues to grow, propelling the quest for knowledge about what exists beyond what we can see. Beyond our observable universe, the nature of the cosmos might differ in numerous compelling and intriguing ways. One possibility is that the regions beyond our perception could contain different galaxies and star systems, some potentially exhibiting completely different structures or compositions compared to those we have observed. For instance, these regions may have galaxies formed under unique conditions that we cannot yet comprehend, leading to a vast variety of cosmic landscapes that include unusual formations or celestial phenomena. Additionally, there could be regions with different physical laws or constants, particularly if theories such as the multiverse hold any credibility. In a multiverse scenario, different universes might manifest entirely disparate conditions, including variations in the fundamental forces, the speed of light, or the behavior of gravity. This would not only change the types of stars and galaxies that form, but could also impact the fundamental building blocks of matter itself, leading to exotic particles or forms of energy that have no counterpart in our observable universe. Moreover, the distribution and behavior of dark matter and dark energy, which dominate the universe's composition, may vary in these unseen regions. While we have a fairly good understanding of dark matter's influence on observable galaxies, its nature and behavior could reveal surprises beyond our current reach. Different concentrations or properties of dark matter could lead to structurally unusual celestial bodies, or even ultimately change the dynamics of cosmic expansion in those areas. Understanding how these regions differ from our observable universe can shed light on questions regarding the origin, evolution, and ultimate fate of everything we know. Each new discovery in the observable universe serves as a reminder that our knowledge is limited, igniting curiosity about what else might await beyond the boundaries of our perception. The potential for different cosmic realities stirs the imagination and fuels the drive for further exploration and discovery. Cosmic inflation is a theory that proposes a rapid exponential expansion of the universe that occurred just moments after the Big Bang, specifically within the first fractions of a second. This theory emerged to address several puzzling questions about the homogeneity and isotropy of the observable universe. According to the inflationary model, the universe expanded at a staggering rate, stretching from subatomic scales to macroscopic distances, smoothing out any irregularities in its fabric. This inflationary phase is thought to have produced the relatively uniform distribution of matter and radiation that we observe today. The significance of cosmic inflation extends beyond our observable universe. One of the key implications of this theory is that the regions beyond the cosmic horizon may also have undergone the same inflationary process, leading to uniformity at large scales. Because inflation happens so quickly, vast regions of space may have expanded beyond our ability to observe or detect, leading to a scenario where significant portions of the universe remain inaccessible to us. This means that even if there are variations in density or structure in those regions, they would be beyond our reach due to the finite speed of light. Moreover, inflation introduces the concept of a potentially infinite universe. If inflation was not localized to our visible universe, but instead affected a much larger expanse, it suggests the possibility of an infinitely vast cosmic landscape beyond what we see. Each region possibly went through its own inflationary process, leading to the creation of separate pocket universes, sometimes referred to as bubbles, each with varying physical properties. If this holds true, it could imply that other parts of the universe might have different fundamental constants, or even different physical laws. The concept of cosmic inflation raises profound questions about the structure and nature of the universe as a whole. It encourages investigations into what lies beyond our observable horizon and invites speculation about the characteristics of realms that remain hidden. This framework enhances our understanding of not only our own universe, but also the potential diversity of realities existing just beyond our observational capabilities. The concept of bubble universes arises from theories related to cosmic inflation and the multiverse. According to these ideas, our universe could be just one of many, each potentially having different physical properties and laws. During the inflationary phase after the Big Bang, certain regions of space could have stopped inflating while others continued to expand, resulting in separate bubbles of space-time that represent distinct universes. These bubble universes might exhibit an array of fundamental differences. For instance, some could have physical constants that vary from those in our universe, leading to variations in the types of matter or forces that exist. Such diversity could result in entirely different forms of galaxies, stars, and potentially even forms of life. This notion expands our understanding of what reality might encompass beyond our own observable boundaries. While the existence of bubble universes is theoretically possible, it remains speculative due to the lack of direct observational evidence. Many scientists are working on ways to gather data that could lend credence to the multiverse theory. For example, cosmic microwave background radiation might hold clues about the inflationary period and indications of collisions between our bubble universe and others. Such cosmic events could leave imprints detectable by current or future observational technologies. The idea of bubble universes tantalizes the imagination and invites inquiry into fundamental questions of existence. Even if we cannot observe these realms directly, exploring the implications of their existence challenges our understanding of the cosmos and encourages further investigation into the fabric of reality itself. Each theory about bubble universes serves as a reminder of the immense unknowns that persist in our quest to understand the universe and our place within it. In regions beyond our cosmic horizon, the laws of physics might differ in ways that challenge our understanding of the universe as we know it. If we consider the possibility of bubble universes or regions within a multiverse framework, each bubble could operate under its own set of physical laws and constants, differing significantly from those in our observable universe. For instance, the strengths of fundamental forces, such as gravity or electromagnetism, might vary, leading to entirely different behaviors of matter and energy. One intriguing scenario involves the cosmological constant, which is associated with dark energy and influences the universe's expansion. In other regions, this constant could take on different values, potentially resulting in varied rates of cosmic expansion. Such differences might also affect the formation and stability of structures such as galaxies and stars, creating environments that diverge dramatically from our familiar cosmic landscape. Additionally, the fundamental particles that constitute matter may exist in different forms or combine uniquely, resulting in alternative types of matter and energy. It is even conceivable that some realms could harbor entirely new forces or interactions yet to be observed within our own universe. This could lead to exotic physical phenomena or conditions that challenge our established scientific theories, pushing the boundaries of our current understanding of physics. While these concepts remain speculative, exploring the potential differences in physical laws beyond our cosmic horizon ignites imaginative inquiry into the nature of reality. They provoke essential questions about the limits of human knowledge and the fundamental structure of the cosmos. As scientists continue to investigate the intricacies of our universe, the possibility that other regions might operate under different rules highlights the ongoing quest to unravel the mysteries of existence itself. The many-worlds interpretation of quantum mechanics is a theoretical framework that suggests every quantum event leads to the branching of the universe into multiple parallel realities. This interpretation was first proposed by physicist Hugh Everett III in the mid-20th century. In conventional quantum mechanics, particles exist in a state of superposition where they can simultaneously inhabit multiple states until observed. The act of measurement appears to collapse this superposition into a single outcome. However, the many-worlds interpretation posits that all possible outcomes actually occur, albeit in separate, non-communicating branches of the universe. According to this interpretation, each decision or random event creates a split in the fabric of reality, leading to a multitude of parallel universes. For instance, if you flip a coin, one universe might see it land on heads, while another sees it land on tails. Each of these outcomes exists in its own distinct universe, meaning that all possible results of quantum measurements coexist and are equally real. One of the most fascinating aspects of the many-worlds interpretation is how it avoids the notion of wave function collapse, a contentious topic in quantum mechanics. By eliminating the need for a collapse, the theory circumvents several philosophical and conceptual challenges associated with observation and measurement. Instead, reality is viewed as a vast, complex structure of branching paths, where every decision and random chance generates new realities. While the many-worlds interpretation remains one of several competing explanations of quantum behavior, it offers intriguing implications for our understanding of reality and the nature of existence. It challenges our perceptions of determinism, free will, and the nature of time, inviting deep contemplation about the consequences of quantum events not just in our universe, but potentially in countless others. As scientists continue to explore the implications of quantum mechanics, the many-worlds interpretation stands as a bold and captivating possibility within the realm of theoretical physics. The concept of parallel universes is deeply intertwined with multiverse theory, which proposes that beyond our observable universe, there exists a vast collection of universes, each with its own distinct properties and laws. While the term parallel universes often refers specifically to the existence of alternate realities that run alongside our own, multiverse theory encompasses a broader range of possibilities, including different forms and structures of universes. In the context of multiverse theory, parallel universes can emerge from several models. One well-known approach is rooted in the many-worlds interpretation of quantum mechanics. Here, each quantum event leads to the creation of a new universe, representing all possible outcomes of that event. This means that for every decision made at a quantum level, a separate universe branches off to account for all potential paths, resulting in an interconnected web of parallel realities. Another facet of multiverse theory comes from cosmological models, particularly those related to cosmic inflation. In this scenario, our universe was just one of many regions that underwent inflation. Each region could expand differently, leading to variations in the underlying physical laws, structures, or constants. These inflating regions could therefore become their own distinct universes within a larger multiversal framework. Additionally, some theories propose categories such as the string theory landscape, where an immense array of possible vacuum states results in a multitude of universes with differing fundamental forces and particle types. Each universe might support unique physical realities and could allow for various configurations of space-time. While each of these concepts illustrates different aspects of multiverse theory, they all share the underlying notion that our universe is not the only reality. The exploration of parallel universes within the broader multiverse framework fuels imaginative inquiries about existence and allows for the possibility of vastly different experiences across multiple realms. This invites us to reconsider our understanding of the universe, reality, and even the nature of life itself within an infinitely complex cosmic tapestry. The theory of eternal inflation extends the traditional model of cosmic inflation, which describes a rapid expansion of the universe shortly after the Big Bang. Eternal inflation posits that this inflationary process does not come to an end everywhere at the same time. Instead, certain regions of space can continue to inflate indefinitely, while others may stop inflating and become observable universes. Essentially, this ongoing inflation can create a scenario where inflating regions are continuously popping into existence, leading to a vast and possibly infinite multiverse. In this framework, the universe is envisioned as a dynamic environment where different regions can experience inflation at different rates. While one part of space may cool and settle into a stable state, forming galaxies and stars, other regions remain in a constant state of inflation. This means new bubble universes are continually forming, each with potentially different physical laws or constants. As a result, eternal inflation supports the idea of a multiverse filled with diverse realities that operate independently of each other. Eternal inflation further reinforces the multiverse concept by suggesting that our observable universe is just one small patch in an expansive cosmic landscape. The consequences of this theory imply that the areas around our universe could host entirely different conditions, making it likely that some might harbor unique structures, fundamental forces, or even different dimensions of time and space. Additionally, the ongoing nature of eternal inflation implies that this process is not merely a one-time event, but rather a dynamic system that shapes the universe continuously. This opens the door to the possibility of an ever-growing multiverse, where each bubble universe represents a snapshot of reality that formed under its specific conditions. In conclusion, the theory of eternal inflation merges the ideas of cosmic expansion and the multiverse, providing a compelling framework for understanding the vast complexities of the cosmos. It challenges the conventional view of our universe as singular and fixed, inviting contemplation about the existence of unobservable realms that may operate under entirely different rules, thus enriching our understanding of reality itself. The landscape multiverse theory arises from string theory, a theoretical framework that seeks to reconcile quantum mechanics and general relativity by suggesting that the fundamental particles of the universe are not point-like, but rather one-dimensional strings. Within the context of string theory, the landscape concept refers to the vast number of possible vacuum states, each corresponding to different configurations of dimensions, physical constants, and forces. These vacuum states determine the properties of the universe that emerge, leading to diverse realities. In string theory, the compactification of extra dimensions plays a crucial role. While our observable universe has 3 spatial dimensions and 1 time dimension, string theory proposes additional dimensions that are compact and not directly observable. The landscape multiverse theory suggests that the way these extra dimensions are configured can yield an astronomical number of distinct vacuum states. In fact, estimates range in the order of 10 to the power of 200 distinct possibilities. Each of these configurations leads to unique physical laws and values for the constants that govern the behavior of matter and energy. As a result, the landscape multiverse theory posits that our universe is just one among an immense tapestry of potential universes, each arising from different vacuum states in this landscape. Some universes might have conditions suitable for the existence of life, while others may lack the necessary structures or forces to support it. This implies that the fundamental characteristics we observe in our universe, such as gravitational strength or the mass of particles, are not universal truths, but rather specific outcomes resulting from the particular vacuum we occupy. The implications of the landscape multiverse theory are profound, pushing the boundaries of our understanding of reality and the nature of existence. It raises questions about the fine-tuning observed in our universe, as many physical properties appear to be precisely calibrated for the emergence of life. In this context, the multiverse provides a potential explanation. If there are a multitude of universes with varying properties, it is statistically likely that at least one universe like our own would have the right conditions for life to thrive. Ultimately, the landscape multiverse theory and string theory introduces a rich and complex view of the cosmos, suggesting that the universe we perceive is merely one of an almost unimaginable variety of realities, each influenced by the fundamental structure of space and the underlying principles of string theory. Detecting evidence of other universes is a complex challenge that pushes the boundaries of our current understanding of cosmology. One of the leading ideas stems from the theory of cosmic inflation, which suggests that our universe experienced an exponential expansion shortly after the Big Bang. This rapid expansion may have resulted in bubbles of space-time, each potentially forming its own universe with different physical laws and constants. While we cannot directly observe these other universes, we can look for clues in our own. One proposed method involves studying the cosmic microwave background radiation, the faint afterglow of the Big Bang. Scientists analyze this radiation for anomalies or patterns that might indicate interactions with other universes. For instance, if two universes collided, it could leave a distinctive imprint on the cosmic microwave background that we can measure. Identifying such irregularities would require highly sensitive instruments and precise data interpretation, but advancements in observational technology lend promise to this pursuit. Another intriguing avenue is the mathematical framework of string theory. This theory suggests the existence of multiple dimensions beyond the four we experience. Some physicists propose that these additional dimensions could provide a pathway for other universes to manifest in our own. Experimental efforts, such as those conducted at particle accelerators, seek to uncover evidence of these extra dimensions which, if detected, might support the existence of a multiverse. Even the concept of dark energy, which is responsible for the acceleration of our universe's expansion, raises questions about the nature of our cosmos. If dark energy behaves differently across various universes, then understanding its properties could offer further insights into the multiverse hypothesis. Though current technology limits us, researchers persistently explore theoretical and observational avenues, inching closer to unraveling the mysteries of our universe and its potential companions. The observable universe is home to some truly astounding large-scale structures, showcasing the vastness and intricacy of cosmic architecture. Among these giants are galactic superclusters, colossal groupings of galaxies bound together by gravity. One of the most prominent superclusters is the Laniakea supercluster, which serves as our cosmic neighborhood. It encompasses around 100,000 galaxies and spans more than 150 million light-years, demonstrating the mind-boggling scales involved in our universe. Beyond superclusters, there are even larger formations known as cosmic filaments. These filaments are made up of galaxies and dark matter, weaving intricate patterns in the universe's large-scale structure. The Sloan Great Wall is a significant example of a cosmic filament, stretching over 100 million light-years in length. Such colossal structures are interconnected, forming a vast web-like architecture with empty voids existing between them. This demonstrates how galaxies are not evenly distributed across the universe. Instead, they form a complex tapestry influenced by gravity and dark matter. Even more extraordinary are the largest structures detected, such as the Hercules Corona Borealis Great Wall. This enormous supercluster measures about 10 billion light-years in size and is considered the largest known structure in the observable universe. Its discovery challenges our understanding of cosmic evolution, as it raises questions about how such vast regions coalesce and what forces govern their formation. These immense structures not only reflect the sheer scale of the cosmos, but also provide crucial insights into the underlying processes that have shaped the universe over billions of years. As scientists continue to study them, they unearth more about the fundamental nature of matter, energy, and the very fabric of space-time itself. The pursuit of knowledge about these colossal clusters fuels our curiosity and desire to understand our place in this grand cosmic scheme. Galaxy filaments and cosmic webs are the result of gravitational interactions and the complex dynamics of dark matter in the universe. These structures emerged during the early stages of cosmic evolution, shortly after the Big Bang. As the universe cooled, matter began to clump together under the influence of gravity. Dark matter, unseen yet pervasive, plays a key role in this process. It does not interact with light, which makes it invisible, but its gravitational pull significantly affects the distribution of galaxies. Over billions of years, regions of slightly higher density in the primordial matter began to attract more matter, forming the seeds of galaxies and clusters. As these local gravitational wells deepened, they attracted even more matter from surrounding areas. This led to the creation of filaments, which are elongated structures resembling cosmic strands. These filaments connect vast clusters of galaxies and create a web-like structure that fills the universe. As the universe continues to expand, the dynamics of matter evolve. Galaxies within the filaments are drawn toward one another, eventually forming clusters at the intersections of these strands. This gravitational hierarchy results in areas of high density surrounded by vast voids, where relatively few galaxies exist. The interconnectedness of filaments provides a framework within which the universe's structure exists, hinting at a beautifully orchestrated cosmic arrangement. Computer simulations and observational data from telescopes further enhance our understanding of this phenomenon. These simulations illustrate how dark matter influences the growth of cosmic structure. Observations from large-scale surveys like the Sloan Digital Sky Survey allow astronomers to detect and map these vast filaments, confirming the theoretical models. Together, they reveal the dynamic processes that give rise to the elegant cosmic web that pervades our universe. Cosmic voids are the vast, empty spaces between galaxies and galaxy clusters, representing some of the largest structures in the universe. These voids can span tens to hundreds of millions of light-years across and are characterized by a significant deficiency in matter compared to denser regions. While they may seem devoid of galaxies, a closer examination reveals that they are not entirely empty. They often contain faint galaxies, dark matter, and diffuse gas, albeit in much lower concentrations than their denser counterparts. The existence of these cosmic voids provides insight into the overall structure of the universe. The distribution of voids and their surrounding filaments and clusters showcases the universe's web-like architecture, a phenomenon that reflects the influence of gravity over billions of years. Voids are essential to our understanding of cosmological evolution because they help scientists probe the origins and nature of cosmic structure formation. By studying voids, researchers can gain insights into the density fluctuations that occurred in the early universe. Moreover, the properties of cosmic voids challenge our understanding of dark energy, the mysterious force causing the accelerated expansion of the universe. The behavior of matter within and around voids can reveal valuable information about how dark energy influences cosmic expansion. For instance, observations of how galaxies move in and around voids may provide clues regarding the mass distribution in the universe and contribute to our understanding of cosmic dynamics. The study of cosmic voids also raises interesting questions about the fundamental nature of the universe itself. They serve as a testing ground for cosmological models, allowing researchers to assess the validity of theories such as the Standard Model of cosmology. As science progresses and observational techniques improve, investigations into cosmic voids continue to unravel the secrets of the universe, enhancing our grasp of the grand tapestry of cosmic evolution. Dark matter plays a crucial role in the formation and evolution of cosmic structures throughout the universe. Despite being invisible and not emitting or absorbing light, dark matter makes up approximately 27% of the total mass energy content of the universe. Its gravitational influence is key to understanding how galaxies, clusters, and even larger structures like superclusters and cosmic filaments form and maintain their shapes. In the early universe, shortly after the Big Bang, matter began to clump together under the force of gravity. While normal matter, which emits light and forms stars and galaxies, began to aggregate, it was the invisible dark matter that provided the framework for this clustering. Dark matter does not interact electromagnetically, meaning it does not collide with regular matter in a way that could dissipate energy. This property allows it to remain gravitationally bound and form massive halos that surround galaxies and clusters. These halos act as gravitational wells, attracting normal matter and facilitating the formation of stars, galaxies, and larger structures. The processes of cosmic evolution and structure formation are intricately linked to the behavior of dark matter. As galaxies merge or interact, their dark matter halos can also collide and merge, which can lead to the growth of larger galaxies and galaxy clusters. Understanding the dynamics of dark matter interactions helps scientists explain phenomena such as the rotation curves of galaxies. These curves reveal that stars orbiting the outskirts of galaxies move faster than expected based solely on visible matter. This suggests the presence of additional unseen mass, attributed to dark matter. Astronomical observations and simulations of large-scale structures further illuminate dark matter's role. By mapping the distribution of galaxies and clusters, researchers can infer the corresponding distribution of dark matter. Projects such as gravitational lensing, which measures how light from distant objects is bent by massive structures, provide direct evidence of dark matter's existence and distribution throughout the universe. As investigators continue to probe the nature of dark matter, they enhance our understanding of its profound effects on the cosmic landscape and the very structure of our universe. Beyond our observable universe lies a realm that is both tantalizing and enigmatic. While we can analyze structures within our cosmic vicinity, speculating on the nature of cosmic structures beyond this observable limit introduces many possibilities influenced by various cosmological theories. One prevalent idea is that conditions surrounding these structures might differ, resulting in distinct formations. For instance, while our universe exhibits a certain distribution of galaxies, clusters, and voids, other regions could have variations in density and arrangement, leading to different large-scale structures. One hypothesis suggests that physical laws might vary in different regions of the universe. If fundamental constants, such as gravitational strength or the speed of light, differ beyond our observable horizon, the evolution of cosmic structures in those areas could produce outcomes that contrast sharply with what we witness nearby. Such variations might lead to exotic astrophysical entities or entirely new types of celestial formations that challenge our current understanding of physics. In addition to potential variations in physical laws, the overall geometry of space-time is a critical factor influencing the structure of the universe. The observable universe appears to be flat, as suggested by measurements of the cosmic microwave background radiation. However, if the universe is indeed infinite and extends far beyond what we can observe, it might incorporate different curvature properties, affecting how cosmic structures develop on large scales. The concept of a multiverse also comes into play, where our universe is just one of potentially countless others, each with its own unique set of physical properties and structure formation processes. In such a scenario, some universes could host bizarre structures or even bizarre rules governing their own cosmic evolution. While these ideas remain speculative, they drive the imagination of scientists and theoreticians, pushing the exploration of the universe's mysteries ever further. The quest to understand these hypothetical cosmic realms beyond our observable universe deepens our appreciation of the vast unknown that lies just out of reach. Dark matter is a mysterious, non-luminous component of the universe that does not emit, absorb, or reflect light, making it invisible to conventional observational techniques. Despite its elusiveness, dark matter is believed to constitute approximately 27% of the universe's total mass energy content. Scientists infer its existence based on the effects it has on visible matter, radiation, and the overall structure of the universe. One of the most compelling pieces of evidence for dark matter comes from the observation of galaxy rotation curves. When astronomers measure the speed of stars orbiting the outer regions of galaxies, they find that these stars move much faster than expected, based only on the gravitational influence of visible matter, such as stars and gas. According to Newtonian physics, they should exhibit a decreasing speed as they move further from the galactic center. However, the observed speeds remain constant, indicating that more mass, most likely in the form of dark matter, exists in the galactic halo than can be accounted for by the stars and gas alone. Another significant piece of evidence comes from gravitational lensing, a phenomenon where light from distant galaxies is bent by the gravity of massive foreground objects, such as galaxy clusters. Observations show that the amount of bending exceeds what could be attributed to the visible mass alone. This discrepancy suggests that there is additional unseen mass exerting a gravitational pull consistent with the presence of dark matter. Furthermore, the distribution of galaxies in the universe follows a web-like structure heavily influenced by dark matter. Simulations of cosmic structure formation, which incorporate dark matter, align closely with observations of the universe's large-scale structure, such as galaxy clusters and voids. These models illustrate how dark matter acts as a scaffold around which visible matter clusters, guiding the formation of galaxies and other cosmic structures. While the exact nature of dark matter remains a profound mystery, various candidates have been proposed, such as weakly interacting massive particles. Research continues, utilizing cutting-edge technologies and experiments aimed at detecting dark matter directly or indirectly. The search for dark matter is crucial, as it not only holds the key to understanding the universe's composition, but also informs the fundamental laws governing the cosmos. Dark matter exerts a profound influence on galaxy formation and the overall architecture of the cosmos. Its gravitational properties are essential in shaping the large-scale structure we observe in the universe today. In the early universe, shortly after the Big Bang, dark matter began to clump together, forming vast halos that provide the gravitational scaffolding upon which ordinary matter could accumulate. This early concentration of dark matter created gravitational wells that attracted gas, dust, and other forms of normal matter, facilitating the birth of galaxies. As galaxies formed, their dark matter halos played a crucial role in determining their sizes, masses, and rotation velocities. Dark matter helps maintain the stability of galaxies by providing additional gravitational pull beyond what is contributed by the visible matter alone. This stability is particularly important because the forces at play during galaxy formation are immense, and the gravitational pull of dark matter allows for the formation of complex structures without causing them to disintegrate under their own dynamics. When galaxies interact or merge, the dynamics of their dark matter halos significantly influence the outcome of these events. For example, during a merger between two galaxies, their respective dark matter halos can collide and merge, along with the visible matter. This interplay can lead to the formation of larger galaxies, which often display different characteristics compared to their smaller predecessors. This merging process is a critical aspect of galactic evolution and contributes to the growth of cosmic structures throughout the universe. On a larger scale, dark matter dictates the overall distribution and movement of galaxies in the universe. The gravitational influence of dark matter creates the cosmic web structure, where galaxies and clusters form along filaments and nodes, with vast voids between them. This gravitational network illustrates how dark matter organizes the cosmos and affects the motion of galaxies over time, shaping the dynamic behaviors of galaxies and clusters as they move through the evolving universe. Dark matter, therefore, is not merely a supporting player in cosmic evolution. It serves as a fundamental force driving the formation and structure of galaxies and the larger cosmos. The search for dark matter particles has led scientists to propose several intriguing candidates, each stemming from different theoretical frameworks in particle physics and cosmology. One of the most widely studied candidates is the weakly interacting massive particle, often abbreviated as WIMP. WIMPs are predicted to have masses on the order of hundreds of GeV, or giga-electron-volts, and would interact through the weak nuclear force and gravity. The theory postulates that they were produced in significant quantities during the early moments after the Big Bang. WIMPs would be challenging to detect directly due to their weak interactions, but certain experiments aim to observe their potential scattering events with normal matter. Another promising category of dark matter candidates is the axion, a hypothetical elementary particle proposed to solve problems related to quantum chromodynamics. Axions are light, slow-moving particles that could make up a considerable portion of dark matter. They are predicted to interact very weakly with other particles, making them quite elusive. Researchers explore the potential for detecting axions through experiments that look for their conversion into photons when exposed to strong magnetic fields. There are also supersymmetric particles, which arise from theories that extend the standard model of particle physics. In these models, each elementary particle has a superpartner with differing properties. Candidates from supersymmetry, like the neutralino, would also possess the necessary characteristics to account for dark matter. Their stability, coupled with interactions driven by the weak force, makes them a compelling candidate in some theoretical frameworks. Finally, primordial black holes offer an alternative explanation for dark matter. These would form from density fluctuations in the early universe, potentially accounting for dark matter's effects through gravitational interactions. While this theory diverges from conventional particle candidates, it remains a point of active research, especially considering the complexities of cosmological evolution. These candidates encapsulate the diverse approaches taken to unravel the enigma of dark matter. Ongoing experiments aim to identify or rule out these possibilities, enhancing our understanding of not only dark matter, but also fundamental physics in the broader cosmos. Each approach holds the promise of advancing scientific knowledge and may lead to profound revelations about the universe's composition and the laws governing it. Dark energy is an enigmatic form of energy that permeates all of space and is responsible for the observed accelerated expansion of the universe. Making up approximately 73% of the total mass energy content of the cosmos, dark energy has perplexed scientists since its discovery. Unlike ordinary matter and dark matter, which exert gravitational attraction, dark energy appears to exert a repulsive force, causing galaxies to move away from each other at an increasing rate. The discovery of dark energy traces back to the late 20th century, primarily through observations of distant supernovae. In the mid-1990s, two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to measure the brightness of type Ia supernovae, which serve as reliable standard candles for determining cosmic distances. By observing these supernovae, the teams expected to find that the universe's expansion was slowing down due to gravitational forces. However, their data revealed a surprising outcome. The supernovae appeared dimmer than anticipated, indicating that they were farther away than previously thought. This led researchers to conclude that the expansion of the universe was not slowing down, but accelerating. The key to understanding this acceleration lies in the concept of dark energy. To explain the observations, scientists introduced dark energy as a driving force behind the accelerated expansion. Various theoretical frameworks were proposed to describe dark energy, with the cosmological constant being one of the most famous models. Proposed by Albert Einstein in the early 20th century, the cosmological constant represents a constant energy density filling space homogeneously. It reflects the idea that even as the universe expands, the energy density remains constant. Other theories have emerged as well, including quintessence, which suggests that dark energy's density may change over time. Despite these various models, the true nature of dark energy remains elusive. Observations of the cosmic microwave background, the large-scale structure of the universe, and other astrophysical phenomena have all contributed to refining our understanding of dark energy. Ongoing research continues to probe this mysterious entity, as unraveling its nature could shed light on fundamental aspects of the universe and the ultimate fate of cosmic evolution. Dark energy holds significant implications for the future of the universe, primarily due to its role in driving the accelerated expansion observed over the past few billion years. As dark energy continues to exert its influence, it shapes the potential scenarios for the ultimate fate of the cosmos. The precise nature of dark energy remains an open question, but its consistent presence suggests several possible futures for the universe. One widely discussed possibility is the Big Freeze scenario. In this model, as the universe expands at an increasing rate driven by dark energy, galaxies will gradually recede beyond our observable horizon. Over immense timescales, star formation will slow, leading to a universe that grows increasingly cold and dark. Existing stars will exhaust their nuclear fuel, and without new stars forming, the vast majority of matter will be left in the form of black holes and white dwarfs. Ultimately, the universe would reach a state of thermodynamic equilibrium, characterized by a uniform temperature near absolute zero, rendering it a desolate and inert expanse. Another scenario is the Big Rip, where dark energy's influence intensifies over time, leading to a runaway expansion. In this model, the accelerated expansion could become so pronounced that it eventually tears apart galaxies, stars, and even atoms. If the energy density of dark energy increases without bound, structures on all scales would disintegrate, culminating in a catastrophic end to the universe. On the other end of the spectrum, some theories propose that dark energy could evolve over time, perhaps leading to a more stable constant state or even transitioning into attractive forces. This change could reverse the current acceleration of cosmic expansion, potentially enabling galaxies to merge and form larger structures once again, leading to a cyclic model of cosmic evolution. As researchers gather more data from observations of supernovae, cosmic microwave background radiation, and galaxy distributions, they aim to refine our understanding of dark energy and its ramifications for the universe. Each of these potential fates underscores the intricate relationship between dark energy and the cosmos, revealing how this mysterious force could ultimately dictate the long-term evolution and destiny of everything within it. The evidence for the expansion of the universe is robust and multifaceted, contributing to our understanding of cosmological dynamics. One of the earliest and most compelling pieces of evidence comes from the observations of galaxies and their redshifts, famously discovered by Edwin Hubble in the late 1920s. Hubble noted that distant galaxies appear to be moving away from us, and the light they emit shows a shift toward the red end of the spectrum. This redshift indicates that the wavelengths of light are stretched as the galaxies recede, a phenomenon consistent with the Doppler effect. Hubble formulated his law, which states that the further away a galaxy is, the faster it appears to be moving away, leading to the conclusion that the universe is expanding. Additionally, the cosmic microwave background radiation, a faint glow left over from the Big Bang, provides further support for this expansion. Discovered in the 1960s, this relic radiation is remarkably uniform, but contains slight fluctuations that reveal information about the early universe's density and temperature. Measurements from satellites, such as the Wilkinson Microwave Anisotropy Probe and the Planck mission, map these fluctuations with great precision. The data suggest that the universe has been expanding since its inception, with the cosmic microwave background serving as a snapshot of the universe when it was only about 300,000 years old, right after it cooled enough for atoms to form. Supernovae also contribute to the evidence for universal expansion, particularly type Ia supernovae, which serve as reliable standard candles for measuring astronomical distances. Observations from the late 20th century showed that the brightness of these supernovae was less than expected, indicating that they were farther away due to the acceleration of the universe's expansion. This discovery was pivotal in confirming that not only does the universe expand, but that the rate of expansion is increasing due to dark energy. Finally, the large-scale structure of the universe, including the distribution of galaxies and cosmic filaments, offers additional evidence for expansion. Current observations reveal that galaxies are not distributed uniformly. Instead, they form a vast cosmic web structure shaped by gravitational interactions. This distribution is a direct consequence of the expansion history of the universe, further reinforcing the paradigm of a dynamically evolving cosmos influenced by the forces at play since the Big Bang. Together, these lines of evidence create a compelling picture of an ever-expanding universe, with each piece contributing to our understanding of its origin and behavior over time. The Hubble constant is a key parameter that describes the rate at which the universe is expanding. It represents the relationship between the distance of a galaxy and its recessional velocity, essentially providing a measurement for how quickly galaxies move away from us as the universe expands. The Hubble constant is typically expressed in kilometers per second per megaparsec, meaning that for every additional megaparsec of distance, a galaxy appears to recede faster by a certain number of kilometers per second. The discovery of this relationship by Edwin Hubble in the late 1920s fundamentally changed our understanding of the universe. His observations revealed that galaxies farther from Earth are moving away at greater speeds, which implies that the universe itself is expanding uniformly in all directions. This expansion can be visualized as the stretching of space itself, with galaxies embedded in that space moving apart over time. Understanding the Hubble constant is essential for determining the scale and age of the universe. By measuring the recessional velocities of various galaxies and their distances through methods such as standard candles or redshift measurements, astronomers can calculate the Hubble constant. This measurement allows scientists to estimate how long the universe has been expanding since the Big Bang, giving insight into its age, which is currently estimated to be about 13.8 billion years. However, it is important to note that recent measurements of the Hubble constant have produced slightly different values depending on the methods used. Observations from the Planck satellite, which measured the cosmic microwave background radiation, suggest a specific value for the Hubble constant, while measurements from large surveys of supernovae and galaxy distributions yield a higher value. This discrepancy has led to ongoing discussions and research in the field of cosmology, as scientists seek to reconcile these differences and better understand the underlying physics of the universe's expansion. Ultimately, the Hubble constant serves as a crucial bridge connecting observations of recessional velocities and distances, solidifying its role as a cornerstone in our comprehension of the expanding universe and guiding future inquiries into its fate. Cosmic acceleration refers to the phenomenon in which the expansion of the universe has been observed to be speeding up over the past several billion years. This counterintuitive behavior suggests that galaxies are moving away from one another at an increasing rate rather than just gradually receding as one might expect from a decelerating expansion under the influence of gravity. The discovery of cosmic acceleration fundamentally shifted our understanding of the universe's dynamics and has significant implications for cosmology. The leading explanation for cosmic acceleration is the presence of dark energy, a mysterious form of energy that permeates space and acts in opposition to gravitational attraction. Dark energy is thought to constitute around 73% of the universe's total energy density. Unlike normal matter, which exerts a gravitational pull, dark energy appears to have a repulsive effect, pushing galaxies apart. The nature of dark energy remains one of the most profound enigmas in modern astrophysics, with various theories proposed to describe its properties, including the cosmological constant, which is a constant energy density filling space uniformly. Observations supporting cosmic acceleration primarily stem from studies of distant supernovae, particularly type Ia supernovae. These supernovae serve as reliable distance indicators, allowing astronomers to measure the expansion history of the universe. When researchers discovered that these supernovae were fainter than expected, it indicated that they were farther away than previously thought, leading to the conclusion that the expansion of the universe was accelerating rather than decelerating. Further evidence for cosmic acceleration is provided by observations of the cosmic microwave background radiation and large-scale structure formation. Measurements of fluctuations in the cosmic microwave background, which is the afterglow of the Big Bang, offer a glimpse into the density and composition of the early universe. The subsequent distribution of galaxies and galaxy clusters across the cosmos aligns with the accelerated expansion scenario, as structures formed from initial density fluctuations influenced by dark energy's presence. Despite extensive research into dark energy and cosmic acceleration, questions remain regarding its true nature and behavior. Ongoing experiments and observational campaigns aim to refine our understanding, potentially revealing new physics that could reshape our comprehension of the universe's evolution and fate. The implications of cosmic acceleration and dark energy extend beyond mere curiosity, delving into profound questions about the underlying fabric of reality itself. The expansion of the universe has significant implications, not only for the regions we can observe, but also for the areas extending beyond our observable limits. As the universe expands, it influences the dynamics and distribution of matter on large scales, and this expansion continues to drive the evolution of cosmic structures both within our observable universe and in the unseen regions beyond it. One of the key effects of this expansion is the notion that regions beyond our observable universe may be receding from us at velocities that exceed the speed of light due to the metric expansion of space itself. This means that light emitted from galaxies in those distant regions may never reach us, forever remaining beyond our cosmic horizon. As the universe continues to expand, more of these regions will recede out of our observable reach, leading to a future where the night sky slowly empties of distant galaxies. This eventual isolation could result in a universe that appears increasingly dark and desolate, altering our perception of the cosmos over cosmological timescales. The effects of expansion also raise intriguing questions about the potential presence of structures beyond our observable universe. While we cannot directly observe these regions, theoretical models suggest that they may contain additional galaxies, clusters, and cosmic filaments similar to those found within our observable limits. However, these structures could evolve differently depending on local conditions, gravitational interactions, and the distribution of dark energy. Such variations could mean that the universe beyond our sight is not merely an extension of what we can observe, but may offer unique characteristics. Furthermore, the expansion rate can influence the fate of the universe itself. If the properties of dark energy evolve or change over time, as some models propose, this could lead to entirely different cosmic scenarios in both the observable and unobservable regions of the universe. For instance, if dark energy were to intensify, it might lead to scenarios like the Big Rip, where cosmic structures are torn apart, affecting the integrity of even the farthest reaches of the cosmos. Ultimately, as scientists continue to explore the fundamental laws governing the universe's expansion, our understanding of its implications, both near and far, will deepen. The uncharted regions of the universe may hold mysteries that challenge our comprehension and provide insight into the very fabric of reality, even if we may never witness them firsthand. The ultimate fate of the universe is a subject of considerable intrigue among cosmologists, with prevailing theories suggesting several potential scenarios based on the universe's expansion and the nature of dark energy. As the universe continues to expand, it will carry galaxies farther from one another. This expansion, driven by dark energy, accelerates over time, leading to the possibility of a big freeze. In this scenario, the universe becomes increasingly cold and desolate, with stars exhausting their fuel and galaxies drifting further apart until they fade into darkness. Alternatively, some models predict a big crunch. In this scenario, if the density of the universe is high enough, gravitational forces may eventually halt the expansion. The universe would then collapse back under its own gravity, potentially resulting in a singular state, similar to the conditions at the very beginning of the universe. This collapse could bring all matter back into an infinitely dense point, possibly leading to another Big Bang and the birth of a new universe. Another intriguing possibility is the Big Rip. This theory posits that if dark energy continues to strengthen, it could tear apart galaxies, stars, planets, and even atoms. In this case, the fabric of the universe itself would ultimately be shredded, resulting in a dramatic disintegration of all structures. Finally, there is the notion of a steady-state universe where expansion continues indefinitely, but the universe remains largely unchanged over time, filled with new matter continually created to fill the gaps left by an expanding cosmos. These theories reflect the complexity and uncertainty surrounding the fate of our universe, inviting further exploration and research in the field of cosmology. Antimatter is a fascinating counterpart to the matter we are familiar with. Every particle of matter has a corresponding antiparticle, which possesses the same mass but has opposite electric charge and quantum numbers. For instance, the antiparticle of an electron, which carries a negative charge, is called a positron, and it has a positive charge. When matter and antimatter meet, they annihilate each other in a burst of energy, usually in the form of gamma rays. This annihilation is a testament to the symmetry and balance between these two forms of existence. The apparent asymmetry or imbalance between matter and antimatter in the universe is one of the most profound mysteries in contemporary physics. When the universe was formed during the Big Bang, theories suggest it should have produced equal amounts of matter and antimatter. However, our observable universe is predominantly composed of matter, leading to the critical question, where did all the antimatter go? This disparity may be attributed to a phenomenon called baryogenesis, which suggests that processes in the early universe favored the production of matter over antimatter, though the exact mechanisms are still under investigation. Various experiments aim to unveil the secrets of this asymmetry. Scientists are exploring particle interactions in high-energy environments to see if tiny differences exist between how matter and antimatter behave. For instance, certain decays of neutral kaons have shown unexpected behaviors that could hint at violations of charge parity symmetry, helping to explain why matter ultimately prevailed. Understanding antimatter also has profound implications for our grasp of the universe as a whole. It challenges our fundamental concepts of physics and could provide insights into the nature of dark matter and dark energy. As researchers continue to explore this enigmatic topic, the quest for deeper knowledge of antimatter might lead us to a fuller understanding of the cosmos itself. The first moments after the Big Bang were marked by extreme conditions that laid the groundwork for the universe as we know it. Initially, the universe was a hot, dense singularity, filled with an almost incomprehensible energy. Within the first tiny fraction of a second, known as the Planck epoch, all four fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, existed in a unified state. As the universe began to expand rapidly or undergo inflation, the temperature and density began to decrease. Just moments later, during a process called cosmic inflation, the universe expanded exponentially, growing from subatomic scales to roughly the size of a grapefruit in only a fraction of a second. This inflationary period smoothed out any irregularities and set the stage for the large-scale structure of the universe. Following this rapid expansion, the universe began to cool sufficiently for fundamental particles, including quarks and electrons, to form. Within the first few minutes, as temperatures approached 1 billion degrees Celsius, fusion began to occur, leading to the formation of light elements such as hydrogen, helium, and trace amounts of lithium. This period, known as Big Bang nucleosynthesis, created about 75% hydrogen and about 25% helium, with only a small fraction of other elements. These early elements provided the building blocks for stars, galaxies, and eventually, the complex structures we observe today. After approximately 380,000 years, the universe cooled enough for electrons to combine with protons, forming neutral hydrogen atoms in a process known as recombination. This led to the release of the cosmic microwave background radiation, a faint glow that fills the universe and serves as a snapshot of the cosmos just after its infancy. These critical moments after the Big Bang not only shaped the early universe but also set the stage for the rich and diverse cosmos we inhabit today. Ultra-high-energy cosmic rays are among the most powerful particles in the universe, with energies exceeding 10 million times that of the particles found in the most energetic man-made accelerators. These cosmic rays consist primarily of protons or heavier atomic nuclei, and their origins remain a captivating enigma for scientists. Understanding where these particles come from could reveal insights into the most extreme astrophysical processes occurring in the universe. Current research suggests that ultra-high-energy cosmic rays may originate from several powerful and highly energetic sources. One leading candidate is supernovae, the explosive deaths of massive stars. These events can accelerate particles to astonishing speeds as they blast material into space. However, the energy required to produce the ultra-high energy cosmic rays we observe is often beyond what supernovae alone can account for. Another potential source is active galactic nuclei, which are related to supermassive black holes at the centers of galaxies. These black holes can emit jets of high-energy particles when surrounding gas and dust are drawn into them. The immense gravitational forces and rapid rotations can accelerate particles to extraordinary energies, making these active galactic nuclei strong contenders for cosmic ray production. Gamma-ray bursts, which are among the most extreme explosions in the universe, are also thought to be significant sources of these energetic particles. The shockwaves from these cataclysmic events can result in particle acceleration processes comparable to those seen in supernovae and active galactic nuclei. Moreover, there are intriguing theories proposing that some ultra-high-energy cosmic rays might originate from the interactions of cosmic rays with the cosmic microwave background radiation, or even from phenomena within the early universe. Research and observation in this field continue to evolve, as scientists look to decipher the mysteries of these energetic particles through extensive observatories and experiments around the globe. The quest to pinpoint the origins of ultra-high-energy cosmic rays not only fills gaps in our understanding of high-energy astrophysics, but also enhances our comprehension of the fundamental forces and processes that shape the universe. Fast radio bursts, which are brief but intense flashes of radio frequency emissions lasting only milliseconds, have sparked immense interest among astronomers and astrophysicists since their discovery in 2007. Though their origins remain largely mysterious, several leading theories attempt to explain these enigmatic signals. One notable hypothesis is that fast radio bursts may be produced by collapsing neutron stars, particularly during events like magnetar flares. Magnetars are a type of neutron star with extremely strong magnetic fields, and when they release energy, they could emit powerful bursts detectable across vast cosmic distances. Some researchers also propose that fast radio bursts could be linked to the destruction of neutron stars in collision with other celestial objects, or even from the processes associated with black holes. Another intriguing idea posits that they might originate from distant galaxies, possibly even from extraterrestrial civilizations, although this latter suggestion remains speculative. The variety in proposed explanations highlights the need for further investigation into these fleeting signals, as each discovery adds a potential facet to our understanding of cosmic phenomena. Fast radio bursts also hold the potential to offer profound insights into the structure and expansion of the universe. The dispersion of these radio signals as they travel through space provides valuable information about the distribution of matter along their path, allowing scientists to measure electron density in the intergalactic medium. This can help refine models of cosmic evolution and shed light on the distribution of matter that is not visible through traditional observational methods. Furthermore, studying the properties of fast radio bursts can help us understand fundamental questions about the universe, such as the nature of gravity, the behavior of matter at extreme densities, and the role of magnetic fields in cosmic evolution. As research intensifies and more fast radio bursts are detected, the potential implications of these phenomena continue to expand, promising to unlock new chapters in our quest to appreciate the complexities of the universe. The Great Attractor is a vast region of space situated within the Laniakea supercluster, which contains our Milky Way galaxy. It is not a singular mass, but rather a gravitational anomaly that influences the motion of galaxies over a broad area, suggesting a concentration of mass on a grand scale. This mysterious gravitational pull was first identified in the 1980s as astronomers observed peculiar motions of galaxies pointing towards a specific zone in the sky, which seemed to be affected by a colossal gravitational force. The Great Attractor is thought to be primarily composed of a massive collection of galaxies, gas, and dark matter. The precise nature and composition of this region remain uncertain, particularly due to its location in the direction of the Milky Way's plane, which obscures our view. Observations indicate that within this massive gravitational center, there is likely a concentration of several thousand galaxies, including the rich and diverse structures present in nearby galaxy clusters. The effect of the Great Attractor includes the movement of galaxies towards it at significant velocities. This motion can be attributed to the immense gravitational influence exerted by the mass aggregated in that region. In broader terms, the Great Attractor is part of the larger cosmic web of structures in the universe, and its gravitational effects are consistent with the overarching interactions in this web that include clusters, filaments, and voids. Beyond its intriguing gravitational dynamics, studying the Great Attractor provides insights into the large-scale structure of the universe, contributing to our understanding of how gravity shapes cosmic phenomena. As astrophysicists continue to investigate this enigmatic region, its study underscores the complexity and interconnectedness of the universe, highlighting how localized gravitational forces can influence the behavior of galaxies across great distances. Inside a black hole's event horizon lies one of the most mysterious and extreme environments in the universe. The event horizon acts as a boundary beyond which nothing, not even light, can escape the black hole's gravitational pull. This fundamental point marks the threshold of no return. Once any object crosses this boundary, it becomes impossible for it to communicate information back to the outside universe. The conditions within the event horizon are profound and convoluted. As one approaches this region, the gravitational forces become immensely strong, resulting in extreme warping of space and time. According to Einstein's theory of general relativity, time itself behaves differently in the vicinity of a black hole. An external observer will perceive time passing slower as one approaches the event horizon compared to someone falling in. This dilation of time creates a fascinating, albeit confusing, dynamic from different perspectives. Inside the event horizon, the traditional laws of physics begin to break down. The gravitational singularity, thought to exist at the center of the black hole, is where matter is theorized to be infinitely dense, and our current understanding of physics is insufficient to describe the conditions. These singularities are points where the curvature of space-time becomes infinite, leading to paradoxes and challenges in reconciling general relativity with quantum mechanics. As researchers strive to understand these extremes, concepts such as quantum gravity are brought into play, indicating a significant gap in our knowledge of fundamental physics. Understanding the nature of what occurs within the event horizon is vital for comprehending not only black holes, but also the fundamental workings of the universe as a whole. As advanced technologies and observational techniques continue to develop, scientists hope to uncover deeper insights into the enigmatic realms of black holes, which could lead to revolutionary breakthroughs in our grasp of cosmic phenomena. White holes are fascinating theoretical concepts that arise from the equations of general relativity, acting as the opposite of black holes. While black holes draw in matter and light, white holes theoretically expel them, functioning as a repulsive force in the universe. The idea suggests that white holes could be the exit points for matter and energy that have crossed into a black hole, creating a one-way passage through which entities could materialize back into the cosmos. The nature of white holes is purely speculative, as none have been observed. Hypothetically, they would be characterized by a singularity at their core, much like black holes. However, instead of matter being compressed into a tiny space, a white hole would be releasing matter, potentially leading to the formation of stars and galaxies. This expulsion of matter would occur in a highly energetic fashion, as the energy would be released at incredibly high velocities, leading to intense radiation. Exploring the implications of white holes opens intriguing questions about the connection between black holes and the broader universe. One thought-provoking idea is that a black hole in one region of space-time might correspond to a white hole elsewhere, potentially linking different parts of the universe. This concept has led to speculation about wormholes, which are theoretical passages through space-time that could connect black holes and white holes. Despite the captivating nature of white holes, significant challenges remain. The laws governing thermodynamics and entropy complicate their existence. For instance, the second law of thermodynamics states that entropy in an isolated system must increase, which poses questions about how matter and energy could be expelled in a manner consistent with this principle. As a result, while white holes remain an alluring possibility within theoretical physics, they currently exist more as mathematical constructs than as physical realities. Ongoing investigations into the nature of black holes and the fabric of spacetime continue to create pathways for understanding such remarkable phenomena. Quasars, or quasi-stellar objects, are some of the most luminous and energetic phenomena in the universe. They are powered by supermassive black holes located at the centers of distant galaxies. As matter falls into these black holes, it forms an accretion disk, heating up to extreme temperatures and releasing vast amounts of energy across various wavelengths, including visible light, radio waves, and X-rays. Quasars can outshine entire galaxies, making them visible across immense distances. One of the most significant aspects of quasars is that they provide a unique glimpse into the early universe. Many of the quasars we observe today are located billions of light years away, meaning that we are looking back in time to when the universe was younger, only a few billion years after the Big Bang. The light we detect from these distant quasars offers crucial information about the conditions and processes occurring in the early cosmos. Quasars are valuable tools for studying the rate of galaxy formation and evolution. Their immense brightness allows astronomers to probe the environment surrounding these supermassive black holes, giving insights into the conditions that facilitated the growth of galaxies during the universe's formative years. Observations of quasars can also help in understanding the distribution of gas and dark matter, as they can illuminate the intergalactic medium they traverse, shedding light on the structure of the early universe. Additionally, studying the spectra of quasars reveals valuable information about the elements present in the early universe and their abundance. This helps scientists piece together the timeline of element formation and the processes that shaped the chemical composition of galaxies. By analyzing these powerful cosmic beacons, researchers not only gain insights into the life cycles of galaxies, but also deepen our understanding of the evolution of the universe itself, making quasars indispensable in cosmological research. The universe is home to some extraordinarily extreme environments that challenge our understanding of physics and the fundamental forces that govern cosmic behavior. One of the most extreme is the core of a neutron star, which is the remnant of a supernova explosion. These stars are incredibly dense, with masses greater than that of the Sun compressed into a volume comparable to that of a city, giving rise to gravitational fields so immense that a sugar cube-sized sample would weigh more than a mountain on Earth. The conditions inside neutron stars are thought to be unlike anything else in the universe, potentially providing insights into the behavior of matter under extreme densities and pressures. Another remarkable environment is found in the vicinity of supermassive black holes at the centers of galaxies. These regions are characterized by intense gravitational forces and immense radiation generated by the accretion of matter, which can be heated to millions of degrees. The event horizon of black holes presents a boundary where the known laws of physics begin to break down, creating conditions that remain puzzling to physicists. Observations of phenomena such as relativistic jets, which are high-energy streams of particles ejected from the area around the black hole, reveal even more about the extreme energies and the dynamic processes at play. Gamma-ray bursts are some of the most energetic explosions observed in the universe, originating from massively energetic events like the collapse of massive stars or the merger of neutron stars. These bursts release more energy in a few seconds than the Sun will emit over its entire lifetime. The extreme brightness and long range of these events allow scientists to study the processes occurring in the distant universe, informing theories of stellar evolution and the conditions present in the early cosmos. Lastly, strong gravitational lensing, caused by massive clusters of galaxies acting as cosmic magnifying glasses, reveals another extreme environment. When light from distant galaxies passes near these dense clusters, it can bend and distort, creating multiple images and exaggerated brightness of the background galaxies. This phenomenon not only showcases the intensity of gravitational fields, but also enables astronomers to probe the distribution of dark matter, offering insights into the structure of the universe and highlighting the interplay between mass and light in the cosmos. Together, these extreme environments provide critical clues to unraveling the mysteries of the universe and the laws governing it. The concept of objects existing beyond our observable universe is a fascinating aspect of cosmology that provokes speculation about the nature of reality. The observable universe is limited to the regions from which light has had enough time to reach us since the Big Bang, specifically about 13.8 billion years ago. However, the actual universe may be far larger, potentially infinite, suggesting the possibility of more extreme objects that we cannot currently observe. Beyond the observable boundary, theories propose that the universe could contain an array of exotic cosmic phenomena. For instance, it may house larger supermassive black holes, possibly formed through the merging of numerous black holes over cosmic time, leading to entities with masses far greater than those found within our observable limits. These black holes could exhibit even more extreme gravitational effects and energetic processes than those we have encountered. Additionally, theories of cosmic inflation indicate that there could be regions of spacetime where the physical laws differ, including the possibility of different constants of nature. These variations might lead to unique structures and formations we cannot perceive, such as universe bubbles with different properties that could harbor novel, exotic states of matter or energy. Another intriguing idea is related to the multiverse hypothesis, suggesting that our universe is just one of many bubble universes within a larger multiverse framework. Each of these bubbles could have distinct physical laws and conditions, possibly allowing for the existence of objects or phenomena that are inconceivable within our own universe. This could include extreme forms of matter or entirely different types of fundamental particles that would behave in radically unforeseen ways. While these ideas remain largely hypothetical, they present captivating avenues for research and exploration in cosmology. As scientists develop better methodologies and technologies to probe deeper into the cosmos, our understanding of the universe, both observable and beyond, may continue to evolve, revealing the remarkable intricacies of existence itself. The prevailing theory regarding the origin of the universe is the Big Bang theory, which proposes that the universe began as an infinitely hot and dense singularity approximately 13.8 billion years ago. According to this theory, a rapid expansion occurred, initiating the cooling process and allowing fundamental particles to form. This expansion is still ongoing, which we observe today as the redshift of distant galaxies. The cosmic microwave background radiation, a faint afterglow of this early expansion, serves as a key piece of evidence, providing a snapshot of the universe just about 380,000 years after the Big Bang. Another intriguing idea related to the Big Bang is the theory of cosmic inflation. Proposed in the 1970s, this theory suggests that within a very brief moment, less than a trillionth of a second, the universe underwent an exponential expansion. This rapid inflation helps to explain the uniformity of the cosmic microwave background and the large-scale structure of the universe we observe today. By smoothing out any irregularities, inflation addresses why the universe appears nearly homogeneous on a large scale. Some alternative theories have emerged that challenge or seek to expand upon the Big Bang model. The cyclic model, for instance, posits that the universe undergoes infinite cycles of expansion and contraction, with each cycle leading to a new Big Bang. According to this view, the universe has no definitive origin or end, but exists in an eternal rhythm of birth and rebirth. This model presents intriguing implications for understanding concepts like time and entropy. Additionally, string theory offers another perspective by proposing that our universe is just one of many in a higher dimensional space. In this framework, the interactions of fundamental strings could lead to the creation of numerous universes, each with its own distinct properties and laws of physics. This multiverse viewpoint raises questions about the nature of reality and our place within a vast and potentially infinite cosmos. As scientists continue to explore and gather data, our understanding of the universe's beginnings may evolve further, potentially leading to revolutionary insights that deepen our understanding of existence itself. Each theory, whether established or emerging, contributes to the complex tapestry of ideas that shapes our quest to unravel the mysteries of the cosmos. The theory of cosmic rebirth, often associated with the cyclic model of the universe, proposes that the cosmos undergoes endless cycles of expansion and contraction, leading to a kind of eternal renewal. In this framework, the universe doesn't have a singular beginning or end, but instead exists in an ongoing process where each cycle starts with a Big Bang-like event and ends with a collapse, sometimes referred to as a Big Crunch. In its basic form, the theory suggests that after the expansion phase, the universe eventually reaches a maximum size. At that point, gravitational forces may become dominant, causing the universe to contract. This era of contraction would lead all matter to come closer together, ultimately resulting in the conditions for a new singularity, much like the one theorized to have existed at the time of the Big Bang. From this singular state, a new expansion could begin, marking the rebirth of the universe in a cycle that can repeat indefinitely. This concept addresses some intriguing questions in cosmology, such as the nature of time and entropy. In a cyclic model, time would not be linear. Every cycle could reset conditions, potentially recalibrating the entropy of the universe. However, critics point out that during each cycle, the universe's entropy tends to increase, raising concerns about whether the universe could smoothly transition from collapse back to a new expansion. Different variations of the cosmic rebirth theory have been proposed to tackle these challenges. Some versions suggest additional mechanisms to counteract increasing entropy, integrating complex ideas from quantum mechanics and string theory to elaborate on how each cycle might occur. Moreover, these models emphasize the potential for new physical processes or phenomena to emerge with each cycle, which could lead to different physical laws or states in the reborn universe. As our observational tools and theoretical frameworks develop, researchers are cautiously exploring the implications of cosmic rebirth. While the notion of an eternal universe challenges conventional understandings of beginnings and ends, it opens exciting paths for further inquiry into the very nature of existence, time, and the fabric of reality itself. The Big Freeze is one of the leading theories about the ultimate fate of the universe, based on the observation that the universe is expanding at an accelerating rate. This concept also connects closely with the behavior of dark energy, the mysterious force driving the acceleration. In this scenario, as the universe continues to expand, galaxies will gradually drift farther apart over vast stretches of time, cooling and transforming the cosmic landscape. As the expansion progresses, stars will begin to exhaust their nuclear fuel. In 1 to 2 trillion years, most stars will have burned out, leading to a universe filled predominantly with white dwarfs, neutron stars, and black holes. The stellar objects that remain would be dimmer and hotter at first, but they will eventually fade into cold remnants. Over an incredibly long timescale, the light and energy produced during star formation will diminish significantly, leaving the universe in a dark, cold state. During the Big Freeze, the temperature of the universe will approach absolute zero as galaxies recede into the vast emptiness of space. Quantum fluctuations may still give rise to occasional interactions, but the overall cosmic environment would become increasingly desolate. This ultimate state, characterized by a lack of significant energy sources, means that life as we know it would become impossible, and any remnants of systems that once had activity would succumb to continued degradation. The Big Freeze represents a scenario devoid of significant physical activity, embodying a universe that becomes cold and lifeless. While this end is eons away, the study of the Big Freeze adds depth to our understanding of the cosmos's long-term evolution and forces us to grapple with profound questions about existence and the nature of time. As more data is gathered and our comprehension of dark energy improves, scientific discourse surrounding various end-of-universe scenarios, including the Big Freeze, will continue to evolve. The Big Rip scenario is a hypothetical end-of-the-universe outcome that emerges from the assumption that dark energy continues to drive the acceleration of the universe's expansion at an increasing rate. If dark energy's effects intensify over time, this scenario suggests that the repulsive force of dark energy could ultimately overpower all forms of gravitational attraction. Initially, galaxies would continue to recede from one another, much like in the Big Freeze scenario, but the expansion rate would accelerate further. As dark energy strengthens, it would begin to affect the structures of galaxies themselves, forcing them to drift apart at increasing speeds. At a certain point, the gravitational bindings that hold galaxies together would weaken, leading to disruptions in galactic clusters. As the expansion persists, the effects would intensify. Stars within galaxies might begin to experience the strain of this accelerating expansion. Over time, the gravitational forces that maintain the integrity of individual stars would be insufficient to counteract the increasing pull of dark energy. Ultimately, the stars would lose their gravitational cohesion, leading to a disintegration of their structures. This dramatic expansion would progress even further to affect the solar systems within galaxies, pulling planets, moons, and other celestial bodies apart. Eventually, even the atoms and subatomic particles that constitute matter could be torn apart, resulting in a universe where all forms of structure disintegrate under the stresses of dark energy's relentless push. If the Big Rip unfolds as described, it would culminate in an event where, at some point in the future, all matter in the universe is torn apart completely, reducing it to its most fundamental components. This scenario raises profound questions about the nature of dark energy and its properties, compelling scientists to investigate its fundamental role in the cosmos and how it influences the universe's ultimate fate. As research progresses, the implications of the Big Rip continue to shape discussions about the long-term evolution of the universe, inviting further exploration into the mysteries of cosmic forces. The Boltzmann brane hypothesis emerges from the field of statistical mechanics, suggesting a thought experiment regarding the nature of consciousness and the universe. It posits that, given the vastness and infinite potential of the universe, it is statistically probable for a single brain to spontaneously form in a state of chaos, complete with false memories and perceptions. This hypothetical brain would come into existence through random fluctuations in a high-entropy environment. The implications of the Boltzmann brane hypothesis are profound and challenge our understanding of reality. If such a brain can exist just by chance, then it raises questions about the reliability of our own existence and consciousness. The universe we perceive may be just a fleeting, random arrangement of particles, while true existence might be far more chaotic and unstable than we realize. This thought experiment intersects with cosmology, particularly in discussions about the nature of time and entropy. It implies that if the universe continues to expand indefinitely, low-entropy regions may become increasingly rare. Eventually, this could lead to a scenario where Boltzmann branes become more common than actual conscious observers, prompting philosophical debates on the nature of knowledge and existence. As we consider our place in the cosmos, the Boltzmann brane hypothesis serves as a stark reminder of the complexity and perplexity of the universe. It challenges the notion of reality and nudges us to examine our understanding of consciousness, existence, and the fundamental laws that govern everything around us. String theory proposes a groundbreaking framework in physics, suggesting that the fundamental building blocks of the universe are not point-like particles, but rather tiny vibrating strings. One of the most captivating aspects of string theory is its requirement for extra dimensions beyond the familiar 3 of space and 1 of time. Depending on the version of string theory, these additional dimensions can be anywhere from 6 to 11, vastly expanding the dimensional landscape of our cosmos. The implications of these extra dimensions are both profound and bewildering. These dimensions are thought to be compactified, meaning they are curled up so tightly that they remain undetectable at conventional scales of measurement. However, their existence could fundamentally alter the laws of physics as we understand them. For instance, the properties of fundamental particles, including mass and charge, could be influenced by the shape and size of these hidden dimensions. As such, They could hold the key to unifying all fundamental forces, including gravity, within a single theoretical framework. Moreover, the existence of extra dimensions may unlock explanations for unresolved questions in physics. For example, they could offer insights into the nature of dark matter and dark energy, mysterious components that make up most of the universe's mass-energy content but remain poorly understood. The interactions occurring within these additional dimensions might provide the missing pieces to our understanding of how the universe behaves on both large and small scales. Finally, exploring the consequences of string theory's extra dimensions invites imaginative possibilities, such as the existence of parallel universes or alternate realities. This tantalizes scientists and philosophers alike, inspiring us to rethink concepts of reality and existence. Delving into these extra dimensions could revolutionize not only our understanding of physics, but also our perceptions of the universe we inhabit. Higher dimensions, as suggested by theories such as string theory, could have a profound influence on the very fabric of the universe and its large-scale structure. In typical three-dimensional space, gravitational and electromagnetic forces operate within a limited framework. However, with additional dimensions at play, the interplay of these forces could undergo significant changes, potentially leading to new forms of matter and energy. These dimensions might allow for additional gravitational interactions that affect how celestial bodies such as stars, galaxies, and clusters form and evolve. One possibility is that the geometry of higher dimensions could impact the behavior of gravitational waves. These waves, caused by catastrophic cosmic events like merging black holes, traverse the fabric of space-time. If there are additional dimensions, they could provide new pathways for these waves, influencing their propagation and detection. This could refine our understanding of cosmic events and enhance our ability to observe phenomena that were previously inaccessible. Considering the expansion of the universe, these extra dimensions might also alter our understanding of dark energy, the mysterious force driving the accelerating expansion of the universe. If higher dimensions interact with known forces in unexpected ways, it could lead to varying effects on cosmic expansion rates and potentially illuminate the nature of dark energy itself. By examining how these added dimensions connect with our own, scientists might uncover ways to explain the universe's accelerating expansion. Additionally, higher dimensions could influence the fundamental properties of particles, contributing to variations in particle behavior at extremely high energies, such as those found in cosmic rays or particle accelerators. These effects may yield insights into unifying the fundamental forces of nature, providing a pathway toward a more comprehensive theory of physics. Ultimately, studying the implications of higher dimensions encourages a re-evaluation of our understanding of the universe, opening doors to new theories and expansive possibilities. The concept of compactified dimensions arises within string theory and other higher dimensional theories, where additional spatial dimensions beyond the familiar three exist but are not readily observable. These dimensions are thought to be compactified, meaning they are curled up into extremely small, intricate shapes, often described mathematically as manifold structures. Because they are so minuscule, typically at the Planck scale, they remain undetected by current experimental methods, which only probe up to subatomic scales. The existence of compactified dimensions holds significant implications for how we understand the fundamental forces of nature and the particles that make up the universe. In this framework, the specific topology, or shape, of the compactified dimensions influences the properties of particles, such as mass and charge. Different compactifications can yield various physical scenarios, potentially explaining why certain particles appear in our universe while others do not. Each unique compactification has its own set of fundamental particles and interactions, suggesting that the characteristics of our universe might be shaped by the way these extra dimensions are configured. Moreover, compactified dimensions might also have a role in determining the fundamental constants that govern the universe. As these dimensions can create a variety of physical landscapes, they may contribute to the so-called landscape problem in string theory, wherein a vast number of combinations exist, each leading to different physical laws. This raises fascinating questions about the anthropic principle and why our universe seems finely tuned for life. Could it be that we are simply situated in one of the many possible configurations of compactified dimensions that allow for such a diverse range of physical phenomena? Lastly, if compactified dimensions interact with known forces, it may yield new physical predictions. For instance, gravitational interactions could extend into these hidden dimensions, altering our perception of phenomena such as gravity and its behavior at different scales. The study of compactified dimensions continues to pose intriguing challenges, pushing the boundaries of our knowledge and offering a window into mysteries that govern the fundamental structure of reality. Gravity in higher dimensions operates under principles that can differ markedly from our familiar three-dimensional understanding. In the context of general relativity, gravity is described as the curvature of spacetime caused by mass and energy. When we extend this framework to higher dimensional spaces, gravity not only influences the three spatial dimensions we perceive, but also interacts with extra dimensions, which introduces fascinating complexities. In higher dimensional theories, such as those posited by string theory, the presence of additional dimensions can alter the behavior of gravitational force. For instance, gravity may be significantly weaker in higher dimensions than in lower dimensions. This is because, in a five-dimensional scenario, gravity can spread out more, diluting its strength. This characteristic could help explain why gravity is so much weaker compared to other fundamental forces like electromagnetism, potentially providing insights into the hierarchy problem in particle physics. Moreover, the geometry of extra dimensions can affect gravitational waves, which are ripples in spacetime generated by accelerating masses. Just as with any wave traveling through a medium, gravity waves might traverse these higher dimensional spaces in unique ways, leading to different propagation characteristics and interactions. Such effects could become observable in experiments designed to detect gravitational waves, thus providing a potential means of probing into the nature of higher dimensions. Additionally, the interaction of gravity with compactified dimensions can lead to phenomena such as gravity leaking into these hidden dimensions. This might explain why we perceive gravity differently than other forces and could also have consequences for the dynamics of our universe. Theoretical explorations of these complex interactions not only challenge our current understanding of gravity, but also open up pathways toward unifying the fundamental forces of nature, illuminating the intricate web that connects the universe's dimensions. The concept of multiple universes existing in different dimensional configurations is a tantalizing idea that emerges from theories such as string theory and the multiverse hypothesis. In this framework, it is proposed that universes can arise from various arrangements or compactifications of higher dimensions, leading to an almost infinite variety of physical realities, each with its own distinct set of laws and constants. These alternative universes could have their own properties, starting conditions, and even different forms of matter and energy. Each universe might manifest specific dimensional characteristics which would influence fundamental forces and particle behaviors. For instance, in a universe with more compactified dimensions, the interactions among particles could differ significantly from those in our familiar three-dimensional space. This variability opens up a spectrum of possibilities, where certain universes may permit complex structures and life, while others might lead to completely different physical phenomena, potentially forming unrecognizable forms. The idea of distinct dimensional configurations also raises philosophical and scientific questions concerning the nature of reality. If these universes coexist, they might be completely separate and isolated, making them beyond our capacity to detect. This aligns with the many worlds interpretation of quantum mechanics, suggesting that every quantum decision branches out, creating varying realities within a vast multiverse. In this scenario, the laws of physics might vary from universe to universe, leading to dramatically different conditions for existence. Exploring the implications of multiple, dimensionally diverse universes expands our understanding of the cosmos and challenges our perception of reality itself. It promotes discussion about the nature of existence, the fine-tuning of physical laws, and the potential for alternate forms of life throughout a broader multiverse landscape. The prospect of other universes, with dimensions configured in ways we cannot currently imagine, captivates both scientists and philosophers, inviting further inquiry into the very essence of the universe we inhabit. Quantum entanglement is a fascinating phenomenon in quantum mechanics, where particles become interconnected in such a way that the state of one particle instantaneously influences the state of another, no matter the distance separating them. When two particles are entangled, their properties are linked. If you measure the state of one particle, you instantly know the state of the other, even if it is light years away. This behavior defies classical intuitions about locality and causality, leading to what Albert Einstein famously referred to as spooky action at a distance. The implications of quantum entanglement extend beyond individual particles and could play a significant role in understanding cosmic-scale phenomena. Entanglement may offer insights into the behavior of particles in extreme conditions, such as those found in black holes or during the early moments of the universe following the Big Bang. As the universe expanded rapidly in the first moments of its existence, entangled particles could have communicated instantaneously, creating correlations that shaped the distribution of matter and energy throughout the universe. Moreover, researchers are investigating whether quantum entanglement contributes to structures at cosmic scales, such as the formation of galaxies or the distribution of dark matter. Some theoretical models suggest that entangled particles might be involved in processes like inflation, the rapid expansion of the universe, which could set the stage for the large-scale structure we observe today. These connections showcase how entanglement could be fundamental to understanding not only microscopic quantum systems, but also the vast intricacies of the cosmos. The study of quantum entanglement in relation to cosmic-scale phenomena also raises profound questions about the nature of reality itself. It challenges our traditional views on separateness and interconnectedness, suggesting that the fabric of the universe might be more intertwined than previously thought. As researchers explore these connections, they venture into a territory where quantum mechanics and cosmology converge, inviting a deeper understanding of the universe and its underlying principles. Quantum tunneling is a remarkable phenomenon in quantum mechanics where particles can pass through energy barriers that they classically should not be able to surmount. In a classical sense, a particle requires sufficient energy to overcome a barrier. If it does not have that energy, it remains confined. However, in the quantum realm, particles are described by wave functions that correspond to probabilities of their locations. This inherent uncertainty allows for the possibility that particles can tunnel through barriers, emerging on the other side, even when they do not possess enough energy to overcome the barrier in conventional terms. To illustrate this, imagine a ball rolling on a surface with a hill in front of it. Classically, if the ball does not have enough energy to reach the top of the hill, it will roll back down. However, in quantum mechanics, there is a non-zero probability that the ball could appear on the other side of the hill without having climbed over it. This effect relies on the wave nature of the particle and is significantly more pronounced at microscopic scales, where quantum effects dominate. Quantum tunneling has profound cosmic implications. For instance, it plays a central role in nuclear fusion, the process that powers stars. In stars, hydrogen nuclei must overcome a significant Coulomb barrier due to their positive charge to fuse into helium. Quantum tunneling allows these protons to penetrate this barrier, enabling fusion to occur at temperatures and energies that are otherwise insufficient. This process is vital for the production of energy in stars and directly influences the evolution of galaxies and the synthesis of heavier elements crucial for life. Furthermore, quantum tunneling could provide insights into phenomena such as cosmic inflation, the rapid expansion of the universe after the Big Bang. Some models suggest that quantum tunneling mechanisms could lead to the creation of bubble universes, contributing to the multiverse concept. In this sense, tunneling does not merely affect individual particles, but could have implications for the formation and evolution of the universe itself. As our understanding of quantum tunneling continues to grow, Its cosmic significance reveals deeper connections between the fundamentals of quantum mechanics and the evolution of the cosmos. The quantum vacuum, often described as the lowest energy state of a quantum field, is a fascinating concept in quantum field theory. Contrary to the classical notion of a vacuum as simply empty space, the quantum vacuum is teeming with activity. It is filled with virtual particles that continuously pop in and out of existence due to the inherent uncertainty of quantum mechanics. These fleeting particles exist for such brief moments that they cannot be directly observed, but their effects can be felt, influencing various physical phenomena. One of the intriguing aspects of the quantum vacuum is its role in energy fluctuations. These fluctuations give rise to phenomena such as the Casimir effect, where two closely spaced conductive plates in a vacuum experience an attractive force due to the suppression of virtual particles between them. This effect illustrates how the quantum vacuum can exert measurable influences on physical objects, demonstrating that empty space is anything but devoid of activity. The implications of the quantum vacuum extend to the larger structure and evolution of the universe. In cosmology, vacuum energy is thought to be linked to dark energy, the mysterious force driving the accelerated expansion of the universe. The energy density associated with the quantum vacuum could contribute to this process, suggesting that the very fabric of space itself has energetic properties that shape cosmic dynamics. As the universe expands, the quantum vacuum may play a crucial role in determining how structures, such as galaxies and clusters, form and evolve over cosmic timescales. Furthermore, the quantum vacuum may have implications for the early moments of the universe following the Big Bang. The rapid expansion known as inflation could be influenced by the high-energy conditions present in the quantum vacuum, leading to the universe's large-scale structure as we observe it today. Ultimately, understanding the quantum vacuum helps bridge the gap between quantum mechanics and cosmology, revealing how the fundamental properties of space and energy influence the universe's history and structure. As we delve deeper into these concepts, we uncover the intricate connections that weave together the fabric of reality. Quantum mechanics and general relativity represent two foundational pillars of modern physics, yet they operate under very different principles. Quantum mechanics describes the behavior of particles and their interactions at extremely small scales, while general relativity explains gravity as the curvature of spacetime caused by mass and energy on cosmic scales. Reconciling these two theories has proven to be one of the most significant challenges in theoretical physics. At cosmic scales, difficulties arise primarily in regions where gravity becomes extraordinarily strong, such as black holes or the very early universe. In these situations, the predictions made by general relativity break down, leading to singularities, points where the laws of physics as we know them cease to function. Quantum mechanics, on the other hand, allows for uncertainty and probabilistic outcomes, which don't easily mesh with the deterministic nature of general relativity. This dichotomy suggests that a more comprehensive framework is needed to unify these two domains. The pursuit of a theory of quantum gravity aims to bridge this gap. Several approaches are being explored, including string theory and loop quantum gravity. String theory posits that the fundamental constituents of the universe are one-dimensional strings rather than points, enabling the description of gravity and other fundamental forces within a single theoretical framework that accommodates both quantum mechanics and the geometric nature of spacetime. Meanwhile, loop quantum gravity attempts to quantize spacetime itself, suggesting that space is made up of discrete structures which may resolve singularities and provide a coherent description of gravity at the quantum level. Additionally, concepts such as holography and the information paradox associated with black holes challenge our understanding of information and its preservation in quantum mechanics. The holographic principle suggests that the information contained within a volume of space can be represented as a theory residing on the boundary of that space, bridging notions of locality and non-locality. As researchers continue to explore these and other avenues, the hope is that a deeper understanding of how quantum mechanics and general relativity interact will emerge, providing a more unified view of the universe that encompasses both the minuscule and the cosmic scales. This reconciliation not only promises to deepen our understanding of fundamental physics, but also sheds light on profound questions about the nature of reality itself. The idea that quantum effects could create connections between distant parts of the universe, or even between separate universes, arises from the unique principles of quantum mechanics, particularly quantum entanglement and non-locality. In quantum mechanics, entangled particles maintain a correlation such that a change in the state of one particle instantly affects the state of the other, regardless of the distance separating them. This phenomenon raises intriguing possibilities about how information and influences could traverse vast cosmic distances. Entanglement challenges traditional notions of locality, suggesting that the interconnectedness of quantum particles transcends familiar spatial boundaries. Some physicists speculate that this could mean information or influence could be shared across significant distances without the constraints imposed by relativistic limits, such as the speed of light. This notion leads to fascinating discussions about the nature of spacetime and causality, posing the question of whether entanglement could serve as a mechanism for broader connections within the universe. Furthermore, when considering the concept of the multiverse, where numerous universes exist with different physical laws or constants, quantum mechanics could provide a framework for interactions between these realms. In certain interpretations of quantum mechanics, like the many worlds interpretation, each quantum event spawns a branching of realities. This suggests that there could be interactions or connections across these branches, potentially leading to influences between distinct universes. These interactions might produce observable effects, although identifying them remains a significant challenge. Also worth noting are theories that propose mechanisms by which entanglement might affect cosmic structures. For example, some researchers suggest that quantum entanglement could play a role in the coordinated behavior of particles and fields in the early universe. This could help explain phenomena like cosmic inflation or the uniformity of the cosmic microwave background radiation. While these concepts are still largely theoretical and face numerous challenges in terms of empirical validation, they highlight the profound implications of quantum mechanics. They encourage us to rethink the structure of the universe and its potential connections, inviting exploration into the very fabric of reality itself. As the dialogue between quantum physics and cosmology evolves, these ideas could pave the way to a more unified understanding of the cosmos. Negative mass is a hypothetical concept that arises in certain theoretical frameworks within physics. It refers to a form of mass that would react in the opposite manner to the forces acting upon it compared to ordinary positive mass. For instance, if a particle with negative mass were to be pushed, rather than accelerating in the direction of the applied force as a positive mass would, it would accelerate in the opposite direction. This counterintuitive behavior challenges our conventional understanding of mass and forces in both classical and relativistic physics. In theory, negative mass could lead to strange and perplexing scenarios. For example, if negative mass exists and interacts with positive mass, it could potentially create peculiar dynamics. A classic thought experiment involves a scenario where a positive mass pulls a negative mass. In such a situation, the negative mass might accelerate towards the positive mass, causing the positive mass to move away from it. This could lead to a runaway effect, where a system could amplify itself indefinitely, raising questions about stability and causality in physical systems. The implications of negative mass extend to discussions about gravity and cosmology. Some scientists have speculated that if negative mass were to exist in the universe, it might influence the dynamics of cosmic structures, possibly providing explanations for phenomena such as dark energy or the accelerated expansion of the universe. Integrating negative mass into our understanding of gravity could redefine fundamental concepts of attraction and repulsion, potentially leading to new insights into the nature of cosmic forces. However, it is essential to note that negative mass has not been discovered or observed in any empirical experiments to date. While certain theories in general relativity and quantum field theory entertain the notion of exotic matter, the materialization of negative mass remains speculative. Nevertheless, Exploring the theoretical framework of negative mass helps extend our imagination regarding the universe's behavior and influences the ongoing quest for a more comprehensive understanding of fundamental physics and cosmological phenomena. Indeed, the possibility of forms of matter with vastly different properties from those we observe is an active area of research in theoretical physics. While we are familiar with ordinary matter, which consists of atoms made up of protons, neutrons, and electrons, there is reason to believe that the universe could harbor exotic forms of matter with unique characteristics. One such example is dark matter, which is thought to make up approximately 26% of the universe's total mass energy content. Dark matter does not interact with electromagnetic forces like ordinary matter, meaning it does not emit, absorb, or reflect light. Consequently, it remains invisible, detectable only through its gravitational effects on visible matter, such as galaxies. The exact nature of dark matter remains elusive, with leading candidates including weakly interacting massive particles and axions, both of which would possess properties and interactions distinct from those of ordinary matter. Additionally, researchers are exploring the concept of exotic matter, which could include substances with negative mass or unusual state configurations. For instance, some theories propose the existence of quark matter, wherein quarks, fundamental constituents of protons and neutrons, exist in a free state rather than being confined within standard atomic structures. This phase of matter could exhibit properties that are dramatically different from the matter we experience daily. Another interesting category is that of supersymmetric particles, which arise in supersymmetry theories. These hypothetical particles would have unique characteristics, including potentially being heavier than known particles and predicted to interact differently with forces. If discovered, they could revolutionize our understanding of fundamental forces and particles. The study of these forms of matter invites speculation about the nature of the universe and its potential configurations. It challenges our traditional views and encourages scientists to search for new physics beyond the standard model. The exploration of exotic matter not only expands our understanding of nature, but also opens up questions about the fundamental principles governing the universe and the potential for phenomena that remain beyond our current observational capabilities. As researchers delve deeper into these mysteries, they inch closer to answering the profound questions about the cosmos and our place within it. Mirror matter is a fascinating theoretical concept that posits the existence of a parallel form of matter that is similar to ordinary matter but possesses opposite properties. The idea emerges from certain extensions of the standard model of particle physics, particularly those involving parity. In physics, parity refers to the symmetrical nature of physical processes, meaning that the laws of physics should remain unchanged when spatial coordinates are inverted. However, when parity is violated, as seen in weak interactions, it leads to intriguing speculations about the existence of a mirror counterpart to ordinary matter. In this framework, mirror matter would consist of particles that mirror the properties of familiar particles, such as electrons, protons, and neutrons, but with reversed interactions and potentially different charges. For example, a mirror electron might interact with mirror protons to form mirror atoms, creating a parallel universe composed of mirror matter. One of the remarkable features of mirror matter is the notion that it would not interact significantly with ordinary matter under normal conditions, making it difficult to detect. This lack of interaction suggests that it could coexist alongside our universe without being observed. The interaction between mirror matter and ordinary matter, if it indeed exists, could be exceedingly rare, primarily occurring through gravitational forces or very specific interactions via hypothetical mediating particles. This notion raises both intriguing and complex questions about the nature of our universe. For instance, if mirror matter contributes to dark matter, its gravitational effects might be present without revealing its existence through electromagnetic interactions. Moreover, some theoretical proposals suggest scenarios where mirror matter could explain certain cosmic phenomena, such as the observed asymmetry between matter and antimatter, or the nature of dark energy. Alternatively, interactions involving mirror matter could potentially lead to observable consequences under particular conditions, such as during high-energy particle collisions in accelerators or in extreme astrophysical environments. While mirror matter remains a speculative concept without empirical confirmation, it offers a tantalizing avenue for exploring the nature of the universe and prompts deeper inquiry into the fundamental forces that govern our reality. As researchers continue to investigate these ideas, the interplay between our familiar universe and potential mirror counterparts may illuminate new aspects of fundamental physics and the cosmos at large. The concept of entire galaxies or cosmic structures composed of exotic matter is an intriguing and speculative idea that arises from our expanding understanding of the universe. Exotic matter refers to hypothetical forms of matter that possess unusual properties which differ significantly from those of ordinary matter. Examples of exotic matter include negative mass, quark matter, and even theoretical forms like mirror matter. While we have yet to observe such materials directly, contemplating their potential existence opens up exciting possibilities regarding the nature of cosmic structures. If exotic matter were to exist, it could influence the formation and evolution of galaxies in unique ways. For instance, consider a galaxy composed of negative mass. In theory, such a galaxy might behave in a radically different manner compared to typical galaxies, as particles with negative mass would react oppositely to gravitational forces. This interaction could lead to a repulsive effect, possibly constructing large structures that disperse instead of clumping under gravity. Such formations would challenge our current understanding of galaxy dynamics and stability. Additionally, the presence of exotic matter could provide alternative explanations for current mysteries in cosmology. For example, if some fraction of dark matter were to consist of exotic matter, it might help clarify discrepancies between observed gravitational effects and predictions made by standard models of galaxy formation. Exotic states of matter, such as quark matter, could lead to unique behaviors under extreme conditions, possibly influencing the rate of star formation or the distribution of matter within a galaxy. Furthermore, if we expand our view beyond individual galaxies to consider larger cosmic structures, the interactions between ordinary and exotic matter could yield surprising outcomes. For instance, a cosmic web formed by a mix of exotic and normal matter might exhibit unusual properties, affecting the overall expansion of the universe or creating novel interactions with gravitational waves. While the idea of galaxies made purely of exotic matter remains in the realm of speculation, it serves to stretch our understanding of cosmic formations and encourages researchers to explore unconventional avenues in theoretical physics. Investigating the potential implications of exotic matter invites us to reconsider the fundamental characteristics of the universe, revealing hidden complexities that could reshape our view of galaxy formation and cosmological behavior. As knowledge of fundamental physics continues to evolve, the contemplation of such exotic structures may increasingly resonate within the broader context of cosmic exploration. Exotic forms of energy, such as dark energy, are thought to play a crucial role in the evolution of the universe. Dark energy is a mysterious force that makes up about 70% of the universe. It is responsible for the accelerated expansion of the cosmos. As the universe continues to expand, the influence of dark energy becomes increasingly significant, driving galaxies further apart and shaping the large-scale structure of the universe. The presence of dark energy alters the dynamics of cosmic evolution. In the early universe, gravity dominated, pulling matter together to form structures like stars and galaxies. However, as dark energy becomes more prominent over time, it counteracts gravitational attraction, leading to an expansion that appears to be speeding up. This has profound implications for the fate of the universe, affecting how galaxies and clusters of galaxies interact and how they eventually evolve over billions of years. Additionally, other exotic forms of energy could influence the universe in different ways. For instance, ideas around modified gravity theories suggest that changes in the gravitational force might exist in ways not yet fully understood. Such theories could impact how dark energy behaves or how structures form and evolve. While dark energy is the most studied, the universe may hold other surprises that await discovery, deepening our understanding of cosmic evolution. Understanding these exotic forms of energy not only transforms how we view the past of the universe, but also challenges our concepts of its ultimate fate. Will the expansion continue indefinitely, leading to a cold and desolate universe? Or might we uncover new forms of energy that change this trajectory? The answers to these questions will fundamentally alter our comprehension of the cosmos and its continuous journey through time and space. Time behaves quite intriguingly near the edge of the observable universe, which is defined by the maximum distance from which light has had time to reach us since the Big Bang. As one approaches this boundary, the effects of cosmic expansion and the nature of space-time begin to come into play, producing phenomena that challenge our everyday experiences with time. Due to the expanding nature of the universe, the farther away something is, the faster it appears to be receding from us. This has a profound effect on how we perceive the passage of time. When observing distant galaxies at the edge of the observable universe, we are effectively looking back in time. Light from these galaxies has taken billions of years to reach us, revealing snapshots of the universe from its infancy. As we peer deeper into space, we find ourselves witnessing events that occurred when the universe was much younger. Moreover, time also runs differently depending on gravitational effects according to the theory of general relativity. The intense gravitational fields near massive objects can warp space-time, causing time to pass more slowly in comparison to regions farther away. While this is more pronounced near black holes or neutron stars, the cumulative effects of such gravity can extend over large cosmic distances, subtly affecting the observation of time in the universe's vast regions. As we study regions near the observable universe's edge, we face intriguing questions about the nature of time itself. Did the universe exist before the instant of the Big Bang? What lies beyond the observable limits? Our understanding of time is tightly interwoven with the structure of space-time, and as science progresses, the knowledge we gain may redefine our perception of how time behaves on a universal scale. Indeed, there are theoretical regions of the universe where time might flow differently, or appear to flow not at all. One of the most striking instances of this occurs near black holes. According to the theory of general relativity, the immense gravitational pull of a black hole distorts space-time significantly. As an object approaches the event horizon, the boundary beyond which nothing can escape, the effect on time becomes extreme. For an outside observer, time seems to slow down for the object nearing the black hole. At the event horizon, time could theoretically come to a standstill. This effect illustrates how time can be perceived quite differently depending on one's position in the gravitational field. Another fascinating scenario arises in cosmic inflation, an early phase of rapid expansion of the universe. During inflation, the universe expanded exponentially. In some models, this could lead to regions where time behaves differently relative to our observable universe. These regions, often referred to as pocket universes or bubble universes, could create localized gravitational effects that alter how time moves compared to other regions. Within such models, freshly created universes could exist with distinct timelines, disconnected from our own temporal flow. The concept of time also raises intriguing implications in the context of quantum mechanics. Some theories suggest the existence of superpositions, where particles can exist in multiple states simultaneously. If such quantum effects extend to the larger universe, it could imply regions where time does not have a uniform flow, potentially leading to instances where traditional notions of past, present, and future could break down. As scientists continue to explore the boundaries of physics, questions regarding the behavior of time in various regions of the universe remain vibrant areas of research. Each new discovery brings us one step closer to understanding whether time is a constant entity throughout the cosmos or a flexible dimension that can warp and shift in intriguing ways. Closed time-like curves are a fascinating concept in theoretical physics and cosmology that allow for the possibility of time travel within a framework governed by general relativity. Simply put, these curves are paths in space-time that loop back on themselves, enabling an object to return to an earlier point in time. This means that if you were to travel along such a curve, you could potentially meet your past self, creating intriguing implications for causality. One of the most famous theoretical models involving closed time-like curves is the Kerr black hole. This type of rotating black hole possesses a region called the ergosphere, where the fabric of space-time is dragged around by the object's rotation. Some solutions of the equations governing these black holes suggest paths that allow an object to traverse back in time. Another scenario involves cosmic strings or wormholes, hypothetical structures that could also lead to closed time-like curves. These solutions tantalize our imaginations as they hint at the possibility of interacting with the past. However, the existence of closed time-like curves raises profound paradoxes. One of the most discussed is the grandfather paradox, where a time traveler might prevent their own existence by interfering with events in the past. This creates complex questions about the nature of cause and effect. Some theoretical physicists have proposed ideas to resolve these paradoxes, suggesting that time travel might only permit self-consistent histories, ensuring that any actions taken would ultimately align with the timeline from which the traveler originated. While closed time-like curves offer solutions that enrich our understanding of the universe's structure, currently there is no empirical evidence that supports their existence. Research is ongoing, and while they remain a compelling aspect of theoretical discussions, they also challenge our perceptions of time and reality itself. As our exploration of the universe deepens, the possibilities enabled by these concepts continue to inspire both scientists and dreamers alike, keeping the door open for potential discoveries about the very fabric of time. Causality, the principle that cause precedes effect, is foundational to our understanding of the universe. However, in extreme cosmic environments, such as near black holes, neutron stars, and potentially in the early universe, this principle may face significant challenges. Gravitational fields in these regions can warp space-time to such an extent that the traditional linear relationship of cause and effect may not hold true. Near black holes, particularly at their event horizons, the structure of space-time is dramatically altered. As an object approaches the event horizon, the gravitational pull becomes so strong that nothing, not even light, can escape. For an outside observer, it seems as though time ceases to pass for the object at the event horizon. In these extreme conditions, it becomes conceivable that events could occur in reverse terms of causality. For example, if a signal were to be sent from inside the event horizon, it would not reach the outside world, complicating any notion of a cause-effect relationship. Furthermore, near the cores of neutron stars, the conditions become even more extreme, with densities surpassing that of an atomic nucleus. The intense gravitation could affect the flow of time, with potential implications for simultaneity. Observers in different regions of the neutron star's gravitational field may disagree on the order of events. Such discord raises questions about linking causes and effects across different reference frames. The early universe also presents a unique landscape where causality can be queried. In the moments following the Big Bang, rapid expansion and extreme conditions could mean that events were not yet defined in a way that we can measure today. The inflationary phase of the universe, during which space itself expanded faster than the speed of light, suggests a scenario where distant regions of space could become causally disconnected. Events occurring in one area may not influence another, challenging our conventional understanding of how cause relates to effect. In all these scenarios, the breakdown of causality underscores the limits of our current theories when confronting the universe's most extreme forces. While general relativity has laid the groundwork for our understanding of cosmic phenomena, these paradoxes invite further exploration of the fundamental laws of nature, inspiring scientists to seek a more comprehensive theory that reconciles the intricacies of time, space, and causality in an ever-expanding cosmos. The concept of time is not universally fixed, and theoretical discussions suggest that there could indeed be universes where time operates differently from our own. In the framework of cosmology and theoretical physics, the fabric of space-time is influenced by the underlying laws governing a given universe. This means that if those laws were different, we might witness entirely distinct manifestations of time. One possibility arises from the idea of varying laws of physics in different universes, as suggested by the multiverse theory. Each universe might have its own set of constants and physical laws, leading to different experiences of time. For instance, in some universes, time may flow at a different rate, or could even be non-linear, allowing for the possibility of simultaneous past, present, and future states. This challenges our standard experience, in which time is perceived as a linear progression from past to present to future. Another intriguing suggestion involves the idea of time as an emergent property rather than a fundamental aspect of reality. In this framework, time could emerge from more basic interactions or configurations, perhaps resembling a complex network of entangled relationships rather than a continuous flow. This could lead to universes where relationships and events determine the experience of time more than a singular trajectory through moments. In such scenarios, different structures of time could manifest based on the specific interactions of matter and energy. The exploration of other dimensions also opens pathways to alternative understandings of time. In string theory, for example, additional spatial dimensions may exist, which could interact with time in ways that differ from our familiar three-dimensional space. These extra dimensions could allow for entirely different temporal concepts within certain frameworks, offering glimpses into how time could function when subject to alternative mathematical structures. As humanity advances in understanding the cosmos, the notion that distinct universes could possess fundamentally different concepts of time continues to intrigue scientists and philosophers alike. Through ongoing research and the quest for a unified theory of physics, we may one day deepen our comprehension of time itself and its potential variability across the tapestry of existence. The universe can be described using various geometrical models, each depicting a different structure of space-time that reflects the distribution of matter and energy within it. The primary geometries considered in cosmology are flat, positively curved, and negatively curved. Each of these geometries has distinct implications for the universe's overall shape and fate. A flat universe follows the rules of Euclidean geometry, where parallel lines never meet, and the angles of a triangle sum to 180 degrees. This model corresponds to a critical density of matter and energy, suggesting that the universe will continue expanding forever, but at a gradually slowing rate. Observations from cosmic microwave background radiation and large-scale structure surveys support the notion that the universe is very close to flat. In contrast, a positively curved universe resembles the surface of a sphere. In this scenario, parallel lines eventually converge, and the angles of a triangle sum to more than 180 degrees. This configuration implies a closed universe, which would eventually halt its expansion and then begin contracting, potentially leading to a big crunch. This model would require a density of matter and energy greater than the critical level. On the other hand, a negatively curved universe is akin to a saddle shape, where parallel lines diverge and the angles of a triangle sum to less than 180 degrees. A negatively curved universe corresponds to a lower density than the critical level, meaning it will expand indefinitely, but at an increasing rate due to dark energy. Determining the geometry of the universe involves careful observations and measurements. Scientists rely on various techniques such as analyzing the cosmic microwave background radiation, which is the afterglow of the Big Bang. By studying its uniformity and slight fluctuations, researchers gain insight into the universe's overall density and geometry. Additionally, observations of distant supernovae help measure the expansion rate, while surveys of galaxy clusters contribute to understanding the distribution of matter. Ultimately, the interplay between these observations enables scientists to refine models of the universe's shape and geometry. By incorporating data from multiple sources, researchers can assess whether the universe's true nature aligns more closely with a flat, positively curved or negatively curved structure, deepening our understanding of how it has evolved and its ultimate fate. Yes, the universe can indeed be finite yet unbounded, a concept that can be visualized through an analogy with the surface of a sphere. In this model, while the surface area is finite, it has no edges or boundaries. This means that if you were to travel in one direction along the surface, you would eventually return to your starting point, having navigated the entire expanse without encountering an end. In a similar fashion, a finite but unbounded universe could be structured in such a way that it wraps back onto itself. For instance, if the universe is curved like a three-dimensional hypersphere, it would mean that the overall volume is finite, yet one could traverse it indefinitely without encountering a physical boundary. This sort of geometric configuration allows for a closed universe, where all spatial directions ultimately lead back to the same points, akin to walking around the Earth without falling off. This concept has deep implications for our understanding of cosmic topology. If the universe were shaped this way, it could influence the distribution of galaxies and cosmic structures. Observationally, we would detect patterns in the cosmic microwave background radiation or the distribution of galaxies that may suggest such a topology. If, for example, the universe were finite but unbounded, we would expect to see specific correlated structures repeated at intervals across vast cosmic distances. Determining whether our universe possesses this manner of geometry requires careful analysis of cosmic data. Observations from the cosmic microwave background, galaxy surveys, and gravitational lensing contribute to this understanding. While current evidence leans toward a flat universe, the possibility of a finite yet unbounded structure remains an exciting avenue of research, as it challenges our conventional notions of space and invites further inquiry into the foundational nature of our cosmos. Such insights into the universe's shape could redefine our approach to understanding its origins and ultimate fate. A hyperbolic or saddle-shaped universe presents a fascinating alternative to our traditional understanding of cosmic geometry. This kind of universe is characterized by a negatively curved space, meaning that as you travel in any direction, the paths diverge similarly to a saddle shape. Visualizing this requires a bit of imagination, as it does not conform to the flat or spherical models we are more accustomed to. In a hyperbolic universe, the geometry allows for a greater amount of space per volume than in a flat or positively curved universe. Imagine a scenario where the angles of a triangle do not sum to 180 degrees. Instead, they total less than that figure. This suggests that the universe can accommodate more distances between points, resulting in a complex and intricate structure. For instance, if you drew two parallel lines in this geometry, they would diverge over distance, causing them to spread further apart rather than remaining equidistant. A hyperbolic universe also has intriguing consequences for the large-scale structure of the cosmos. Because space is negatively curved, light rays traveling across vast distances would behave differently than in flat or positively curved spaces. We might observe more paths for light to reach an observer, potentially leading to what are known as multiple images of distant astronomical objects, a phenomenon that could reveal itself through gravitational lensing. Observationally, signs of a hyperbolic universe would appear in the distribution of galaxies and the cosmic background radiation. One might see an abundance of large voids interspersed with clusters of galaxies, creating a more chaotic arrangement than the patterns expected in a flat or closed universe. The expansion rate of such a universe would also be influenced by dark energy, likely leading to perpetual expansion as it continues to grow increasingly negative, reinforcing the hyperbolic nature of its geometry. As scientists investigate the cosmos, understanding and confirming the nature of our universe's shape will require meticulous observations and data analysis. The implications of a hyperbolic universe challenge our conventional perspectives and invite deeper inquiries into the complex interplay of gravity, expansion, and cosmic structure that defines our reality. The shape of the universe has profound implications for what lies beyond our observable region, significantly affecting our understanding of cosmology and the potential nature of the cosmos as a whole. Our observable universe is limited by the distance that light has had time to travel since the Big Bang, creating a spherical volume around us. However, what lies beyond this observable sphere can vary dramatically depending on the universe's overall geometry. In a flat universe, which aligns closely with what current measurements suggest, the implications for the region beyond the observable universe are relatively straightforward. Such a universe could extend infinitely, with an endless continuation of the structures and patterns we see within our observable limits. This would imply that galaxies, cosmic phenomena, and structures continue infinitely, suggesting a uniformity in the distribution of matter across vast distances. This flat geometry allows for the possibility of more similar regions of the universe repeating, reinforcing the idea that the laws of physics are applicable everywhere. Conversely, if the universe were positively curved, like the surface of a sphere, this could lead to a closed structure. In this case, there might be a finite volume of space beyond our observable limits, which eventually loops back on itself. Traveling far enough in one direction could, theoretically, allow for a return to the starting point, akin to circumnavigating the Earth. Such a topology could imply that different regions of the universe are interconnected, potentially leading to observable consequences, wherein distant galaxies might repeat themselves in patterns. In the scenario of a hyperbolic or saddle-shaped universe, the implications are even more complex. A negatively curved universe could result in a vast expanse of space where the structures within it remain spaced apart and diverge. The topology might lead to greater complexity in the arrangement of galaxies, possibly resulting in large voids and clusters existing in a manner that defies straightforward categorization. In this case, the nature of the cosmos beyond our observable region might consist of an intricate tapestry where familiar cosmic rules manifest differently, reshaping our understanding of cosmic architecture. In all these scenarios, the shape of the universe profoundly influences not only what constitutes the cosmos beyond our visible range, but also the broader understanding of its structure, dynamics, and fundamental laws. As researchers gather more data from cosmic observations, the quest to determine the true geometry of the universe will continue to shape our comprehension of what lies beyond, inviting us to ponder the vast mysteries that remain undiscovered. Yes, the universe could indeed possess a more complex topology, such as that of a torus or a Klein bottle. These shapes present interesting alternatives to simple geometries, allowing for unique configurations that challenge our understanding of space and how it may be structured on a cosmic scale. A toroidal universe, shaped like a donut, implies that if you travel in one direction, you could eventually return to your starting point without ever encountering an edge or boundary. In a three-dimensional toroidal topology, moving in one direction would connect you back to your original position after making a complete loop around the whole of the torus. This kind of structure allows for a finite volume, meaning it contains a limited amount of space, while still being unbounded. Consequently, this topology could lead to intriguing patterns in the distribution of galaxies, where repeated formations or structures might be observed in multiple locations due to this looping nature. On the other hand, a Klein bottle presents an even more complex notion. This shape cannot be fully realized in three-dimensional space without self-intersections. It exists only in four-dimensional space. A Klein bottle has no distinct inside or outside, challenging traditional notions of dimensionality and boundaries. In a cosmological context, if our universe were to resemble a Klein bottle, it could imply that traveling through space might lead to unexpected paths or connections that defy our conventional understanding of paths and distances. The implications of this kind of topology could allow regions of the universe to be interconnected in non-intuitive ways. The study of complex topologies like these can help explain certain cosmic phenomena or features observed in the universe. For instance, if the universe was shaped like a torus, it might lead to peculiar gravitational effects or patterns in the cosmic microwave background radiation, where repeated structures could emerge. Research into these ideas involves analyzing how the properties of such topological shapes might align with observations, and lets scientists reconcile data regarding cosmic expansion and distribution. Understanding the topology of the universe remains a vibrant area of research, inviting continued exploration into the intricate possibilities that shapes like the torus and Klein bottle present. By delving deep into these complex configurations, scientists hope to uncover the true nature of our cosmos, offering exciting insights into its structure and behavior beyond the observable realm. The simulation hypothesis posits that what we perceive as reality might actually be a sophisticated simulation created by a more advanced civilization, resembling the complex digital worlds depicted in science fiction. This intriguing idea suggests that the universe we inhabit, including all of our experiences and interactions, could be the product of computational processes running in a higher dimensional environment, akin to a powerful computer. One of the most prominent proponents of this hypothesis, philosopher Nick Bostrom, framed it as a trilemma, proposing that at least one of the following propositions must be true. Civilizations become extinct before achieving the technological capacity to create realistic simulations. Advanced civilizations are not interested in creating such simulations, or we are almost certainly living in a simulation ourselves. If the last proposition holds true, it implies that the chances of us being one of the many simulated beings far outweigh the possibility of our reality being the base reality. Applying the simulation hypothesis to our universe raises profound philosophical and scientific questions. If we were indeed living within a simulated environment, it might imply that the physical laws and constants we observe are not fundamental truths, but rather parameters set by the creators of the simulation. This could mean that the universe, while appearing vast and complex, is based on coded rules that allow for the emergence of life, consciousness, and the observed cosmos. The implications of such a hypothesis extend into realms of spirituality and existential inquiry. If our experiences in this universe are merely simulations, it challenges our understanding of consciousness, free will, and the nature of existence itself. Are our thoughts and feelings genuine, or are they simply constructs within an elaborate program? This speculation could encourage further exploration into the essence of reality, prompting investigations into what defines our experiences and whether there is a deeper reality beyond the simulation. While the simulation hypothesis offers a tantalizing perspective on the nature of our universe, it also remains highly theoretical, lacking direct empirical evidence. Despite this, advancements in technology, such as virtual reality and artificial intelligence, continue to push the boundaries of what we consider reality, prompting ongoing debates about the implications of existing within a potential simulation. As scientists and thinkers delve deeper into the nature of consciousness and the structure of the universe, the question of whether we are part of a grand cosmic simulation invites reflection and exploration of our place in the cosmos. The notion that our observable universe could be a small part of a vast cosmic simulation is a compelling extension of the simulation hypothesis. This idea suggests that while we perceive a universe of incredible complexity and depth, it might only represent a fraction of a far grander simulated reality designed by a more advanced civilization. In this framework, our experiences, physical laws, and the very structure of space-time could be elements within a meticulously crafted simulation. If our observable universe exists within such a framework, it would imply that the expansive cosmos we see is just a localized projection of a much broader digital landscape. The parameters and rules governing our universe, from the forces of nature to the behavior of subatomic particles, could be sophisticated algorithms constructed for the purposes of exploration, experimentation, or even entertainment by the creators of this simulation. This raises questions about the limitations of our understanding, suggesting that what lies beyond our observable limits may be as intricate and complex as what we currently perceive. Such a scenario would mean that scientific inquiries are ultimately constrained by the boundaries of the simulation. Our attempts to interpret and understand the nature of reality could be based upon a limited dataset, akin to attempting to comprehend a vast book by reading only a few chapters. This leads to intriguing implications regarding future discoveries. If parts of the universe exist outside the simulation or are merely off-screen, our quest for understanding could continually reveal wonders previously unimagined. Additionally, the simulation hypothesis touches upon fundamental philosophical questions regarding consciousness and existence. If our universe is a small part of a larger simulation, are we merely players within a program, or do we have autonomy and agency? What does it mean for our identity, personal experiences, and interactions if they exist within such confines? This could challenge our perceptions of free will and the essence of what it means to be conscious. While the idea remains speculative and currently lacks tangible evidence, it opens a rich field of inquiry as scientists and philosophers explore the implications of advanced technology, artificial intelligence, and their potential connections to the fabric of reality. The quest to understand whether our universe is indeed a mere portion of a grand cosmic simulation invites both scientific and philosophical exploration, prompting profound reflection on the nature of existence itself. In a simulated universe, the laws of physics could differ significantly from those of the host universe, depending on the parameters and limitations set by the creators of the simulation. These differences could manifest in various ways, influencing everything from fundamental constants to the behaviors of particles and forces that govern the simulated reality. One potential difference lies in the fundamental constants of nature, such as the gravitational constant or the speed of light. In a simulation, these constants could be altered, either intentionally or as a reflection of the limitations of computational resources. For instance, if the creators wanted to simulate different physical scenarios, they might adjust these values to allow for new phenomena or to create distinct environments for specific purposes. This would result in a universe that behaves differently than what we observe in our reality, leading to entirely new physical behaviors and interactions. The laws of thermodynamics, which govern the flow of energy and the direction of processes, might also be subject to customization in a simulated universe. For example, in a simulation, certain thermodynamic principles could be relaxed or modified, resulting in seemingly impossible outcomes, such as perpetual motion machines or alterations in entropy. Such changes would present exciting opportunities for exploration within the simulation, but could fundamentally defy what we recognize as the laws of our universe. Moreover, the structure of space-time could differ in profound ways. In a simulated environment, the dimensions may be manipulated, allowing for non-Euclidean geometries that defy our understanding. This could enable faster-than-light travel, rewrites of causal relationships, or even the existence of shortcuts between distant points in the universe. Such variations would drastically change the perception of space and time, offering a playground of possibilities that challenge our current scientific framework. Additionally, the behavior of particles and fields might follow specific coding designed to reflect a more simplified or alternatively complex reality. Quantum phenomena could be programmed to exhibit different properties, such as variations in entanglement or superposition states, which could impact the very foundations of quantum mechanics as we know it. This would ultimately affect the nature of information, measurement, and reality within the simulated universe. As scientists and philosophers contemplate the implications of a simulated universe, they grapple with questions about the nature of reality, the limits of our knowledge, and the creative potentials of advanced technologies. By examining how the laws of physics could differ in such a scenario, we deepen our understanding of the universe we inhabit and the fundamental principles that govern existence itself. The concept of nested levels of simulated universes, essentially simulations within simulations, raises fascinating questions about complexity, existence, and the nature of reality. This idea suggests that within a primary simulation, there could be sub-simulations, each with their own sets of rules, physics, and parameters, creating a hierarchy of realities. In a nested simulation, each layer could potentially possess its own laws of physics, which may vary from those in higher or lower levels. For instance, a universe that operates under certain constants and fundamental laws might serve as a testing ground for different scenarios created by even more advanced civilizations. This hierarchical structure could allow for extensive exploration of possibilities. Each simulation could experiment with variations in physical laws, the nature of consciousness, or even the outcomes of historical events. Such nesting of simulations would also evoke questions about the origins of consciousness and experiential continuity. If beings within the simulated universes possess self-awareness and agency, do they perceive their reality as real, despite being part of a larger construct? What happens to the consciousness or identities of entities that exist within these hierarchies? This could lead to philosophical implications about identity and existence, because individuals in lower-level simulations might be unaware of higher layers or could view their reality as the ultimate existence. Technologically, creating nested simulations would require significant computational power. The complexity grows rapidly, as the fidelity of each nested simulation could have to maintain coherence with the larger reality. This raises thoughts about the limits of technology and resources available to the advanced civilization orchestrating these simulations. Perhaps creating nested levels could also result in more efficient processes, enabling the simulation of entire universes while utilizing fewer resources by only simulating aspects that are necessary for the experiences of the inhabitants. In addition, this idea could lead to intriguing scenarios where feedback loops exist between simulations. Actions taken in one level may have repercussions in another. For example, events in a lower-level simulation might influence the conditions or scenarios run by the higher-level simulation. This interplay could create a complex tapestry of causality that challenges our traditional notions of linear progression and causative relationships. While the idea of nested simulations remains speculative, it serves as a thought-provoking framework for contemplating the complexity of reality, consciousness, and technology. Engaging with these concepts encourages reflection on the very nature of existence and the potential for realities that extend far beyond our current understanding of the universe. As we continue to explore the mysteries of physics and technology, the implications of such nested simulations invite creative and philosophical inquiry into our place within the cosmos. The question of whether our universe is a simulation has fascinated scientists and philosophers alike. To explore this intriguing idea, researchers propose several methods for detecting signs of a simulated reality. One approach focuses on identifying anomalies or inconsistencies in the laws of physics. If our universe were a simulation, there might be detectable limits to physical phenomena, much like the performance limits in computer graphics. For instance, scientists might look for unexpected granularity in space-time or unconventional behaviors in fundamental particles. Another avenue involves the search for computational artifacts. If our universe operates within a vast computer system, there could be detectable glitches or shortcuts similar to those found in virtual simulations. Researchers might explore the behavior of cosmic rays, high-energy particles that travel vast distances. A significant deviation from expected patterns could suggest underlying computational limits, indicating we might live in a simulated environment. Quantum mechanics also presents unique possibilities. Quantum entanglement and the observer effect offer ways to interrogate the nature of reality. If reality functions similarly to a sophisticated computation, perhaps the outcomes of quantum experiments could yield clues about the presence of a simulation. Some scientists have theorized that certain fundamental aspects of quantum mechanics might serve as hints that we are perceiving a constructed reality rather than a direct experience of the universe. Mathematicians and physicists are also considering the implications of information theory. All physical processes can be encoded as information. If our universe carries an underlying information structure, it could indicate a simulation. This line of thinking prompts researchers to investigate the universe at its deepest levels, seeking out signs that our reality operates more like software than we might typically assume. The speed of light is widely regarded as a universal constant, with a value of approximately 300,000 kilometers per second in a vacuum. This constancy underpins many of our fundamental theories in physics, particularly Einstein's theory of relativity. However, the notion of varied speeds of light in different regions of the universe sparks captivating discussions within scientific communities. Some theories propose that light could behave differently under specific conditions, particularly in realms marked by intense gravitational fields. In the vicinity of black holes, for instance, the extreme curvature of spacetime can influence how light travels. While this does not change the speed of light in a vacuum, it affects its passage, altering perceptions of time and space. As light approaches a massive object, its apparent speed might seem reduced to an outside observer due to the gravitational effects. Another intriguing concept arises from the idea of varying physical constants throughout the universe. Some researchers suggest that constants like the speed of light could have been different in the early universe or might fluctuate over vast cosmic distances. These hypotheses could lead to scenarios where, over extensive timescales or vast distances, light behaves differently due to changes in the fundamental laws of physics. Furthermore, theoretical frameworks, including certain interpretations of string theory or varying speed of light theories, explore the possibility of light's speed being influenced by the environment or unseen dimensions. While these ideas remain speculative and have yet to be confirmed through empirical evidence, they encourage a deeper investigation into the fundamental principles governing our universe. Such inquiries remind us of the vast unknowns that still lie ahead in our understanding of cosmic laws. If fundamental constants, such as the gravitational constant, varied across the universe, it would have profound implications for our understanding of physics and cosmology. The gravitational constant dictates the strength of gravity, which in turn governs the formation and behavior of stars, galaxies, and even the structure of spacetime itself. A variation in this constant could lead to dramatically different physical phenomena in different regions of the universe. For instance, a weaker gravitational constant could result in less stable star formation processes. Stars may burn through their hydrogen fuel much more rapidly and could struggle to hold onto the mass needed to avoid dispersing into space. Galaxies might take on radically different shapes or even fail to form altogether. On the other hand, a stronger gravitational constant would pull matter together more tightly, possibly leading to more rapid star formation, but also resulting in denser environments that could become more extreme. Moreover, variations in fundamental constants could challenge the laws of physics as we understand them. The delicate balance of forces that govern everything from atomic interactions to gravitational binding could become unstable. The unification of forces, a significant goal in theoretical physics, would be complicated if these constants were not uniform. This could lead to scenarios where fundamental interactions are inconsistent, making consistent physical laws difficult to define. Lastly, the potential for differing constants might invite new realms of exploration in theoretical physics. It could indicate that our universe is just one of many, possibly existing within a multiverse framework, where each universe has its own distinct set of physical laws and constants. Such revelations would redefine our understanding of complexity and diversity in the cosmos, highlighting the intricate tapestry that makes up existence itself. A universe with different numbers of spatial or temporal dimensions would exhibit vastly different characteristics compared to our own three-dimensional space and one-dimensional time framework. The familiar laws of physics, which are closely tied to the four dimensions we experience, would transform dramatically if either spatial or temporal dimensions changed in number. In a universe with more than three spatial dimensions, the rules of gravity and motion would alter fundamentally. For example, in a four-dimensional space, gravitational attraction could behave differently, potentially allowing for more complex interactions between masses. Objects might find it easier to escape gravitational pull, leading to radically different structures for galaxies and planetary systems. The concept of distance, volume, and surface area would expand into more complex geometries, challenging our intuitive understanding of space. Conversely, if there were fewer spatial dimensions, such as only two, the dynamics of everyday life would change significantly. Motion would be restricted to planes rather than volumes, affecting everything from the way objects collide to how they can orbit one another. Strongly interacting systems, like those observed in particle physics, could behave notably differently, resulting in simpler structures and perhaps fewer existing forms of matter. The implications of altering temporal dimensions are equally fascinating. If there were two dimensions of time, it could lead to multiple temporal paths and timelines. Causality, as we understand it, would be challenged, allowing for complex interweavings of events without clear linear progression. A universe with one less dimension of time could confine phenomena to more static states, potentially altering the nature of change itself. These changes in dimensionality could yield different forms for the fundamental forces of nature, and challenge the very principles of quantum mechanics and relativity. The exploration of such alternative universes encourages deeper contemplation of our own reality's structure and dimensions that we often take for granted. The weak nuclear force plays a crucial role in the universe, governing processes such as beta decay and playing a pivotal part in nuclear reactions within stars. If the weak nuclear force did not exist, the consequences would be profound and far-reaching, dramatically altering the makeup and behavior of matter. In the absence of the weak nuclear force, certain types of particles, particularly neutrinos and quarks, would behave differently. Beta decay, a process by which a neutron transforms into a proton while releasing a weakly interacting particle called a neutrino, would be impossible. This fundamental transformation is essential for the stability of atomic nuclei, and without it, elements such as carbon, nitrogen, and oxygen might not form. This would lead to a universe lacking many of the essential building blocks for life as we know it. With the weak nuclear force absent, the dynamics of stellar evolution would shift dramatically. Stars, which rely on fusion processes, would struggle to produce heavier elements. The process of helium burning, for example, relies on weak interactions to fuse helium into carbon. Without the weak nuclear force, the life cycle of stars could be truncated, potentially preventing the formation of key elements necessary for chemical complexity and biological processes. Moreover, the universe would fundamentally differ in terms of its temperature and structure. The balance of forces that governs the early universe's evolution would be disrupted, affecting the matter distribution and possibly leading to a universe that would either collapse or expand at a different rate. The absence of the weak nuclear force might also prevent the formation of galaxies or large-scale structure, fundamentally altering the cosmological narrative we currently understand. Without the weak nuclear force, the universe would likely be a much simpler and perhaps inhospitable place, lacking the rich diversity of chemical elements and complex structures necessary to support life. The intricate tapestry of interactions and reactions that supports the vibrant universe we inhabit would be significantly altered, fundamentally redefining existence itself. The concept of universes with entirely different sets of fundamental particles is a fascinating aspect of theoretical physics and cosmology. In our universe, fundamental particles like quarks, electrons, and neutrinos combine through the forces described by the standard model of particle physics to create all matter. However, the idea of alternate universes suggests that if the fundamental building blocks of nature were different, the nature of reality itself would be dramatically altered. In such universes, the properties and behavior of matter could vary significantly. Without the current set of particles, the stability of atomic structures would be uncertain. For instance, if a universe possessed heavier or lighter versions of particles, the interactions between them would lead to entirely different elemental compositions and physical phenomena. This could result in matter that behaves in ways completely alien to our comprehension, potentially affecting everything from the formation of molecules to the behavior of solid matter. Moreover, the forces that govern particle interactions could also differ in a universe populated with different fundamental particles. The electromagnetic, weak and strong forces may operate under various principles or intensities. This shift would have downstream effects on the formation of complex structures, such as galaxies or planetary systems. If these structures do form, they might evolve under rules that seem completely foreign to us, potentially yielding worlds with no resemblance to our own. Additionally, the implications for life as we know it would be profound. The specific characteristics of particles in our universe, such as their mass and charge, are critical for the chemistry that allows life to develop. If alternative particles with different properties existed, the conditions for life might be severely altered or entirely absent. Thus, while the notion of universes with different particles allows for speculation about the nature of existence, it also underscores the delicate interplay of forces and components that make our universe uniquely suited for the emergence of life. Advanced civilizations attempting to communicate across cosmic distances would face the formidable challenges posed by the vastness of the universe and the limitations of light-speed transmission. Given the enormous distances between stars and galaxies, achieving effective communication would require innovative approaches. One primary method could involve the use of electromagnetic signals, such as radio waves or laser beams. These forms of communication travel at the speed of light, allowing signals to traverse interstellar distances, albeit with significant time delays. For example, a message sent from a civilization near a distant star could take years or even centuries to reach its intended recipient on another star system. To compensate for the time lag and ensure messages reach their destinations, civilizations might employ advanced coding techniques that allow for the compression of information. The use of pulsars or quasars as cosmic beacons could also play a role. These naturally occurring astronomical sources emit consistent signals that could serve as reference points for interstellar communication, helping civilizations synchronize their messages with one another amid the vast timescales involved. Another intriguing possibility lies in the use of particle-based communication methods, such as quantum entanglement. If advanced civilizations harnessed the phenomenon of entanglement, they might achieve instantaneous communication regardless of distance. Though our current understanding of quantum mechanics limits practical implementation, future advancements could leverage these principles to exchange information in ways that defy the constraints of conventional electromagnetic communication. In addition to technological advancements, successful communication would require a mutually understood language or code transcending linguistic barriers. This endeavor might necessitate the creation of universal symbols or mathematical constructs that convey fundamental scientific concepts, establishing a common ground. The quest for interstellar communication not only highlights the ingenuity of advanced civilizations, but also reflects the collaborative spirit that may emerge from the shared pursuit of knowledge across the cosmos. The idea of natural phenomena transmitting information faster than light challenges the foundation of physics as established by Einstein's theory of relativity, which prohibits such occurrences. According to this theory, nothing can travel faster than the speed of light in a vacuum. However, scientists have speculated about certain phenomena that might suggest ways in which information or effects could be perceived rapidly enough to mimic superluminal communication. One intriguing possibility involves quantum entanglement, a phenomenon where pairs of particles become correlated in such a way that the state of one particle instantly influences the state of the other, regardless of the distance separating them. This has led to discussions about whether entangled particles could be used for instantaneous information transfer. However, it's important to note that while changes in one entangled particle are correlated with another, this does not allow for the transmission of usable information faster than light, as the measurement results are inherently random and cannot be controlled. Certain interpretations of theoretical physics have proposed hypothetical scenarios involving warp drives or wormholes. These concepts suggest that manipulating spacetime could permit effective communication across vast distances while circumventing the light speed limit. In such cases, information could be encoded and transmitted through regions of spacetime that fold or connect disparate points in the universe, allowing for incredibly rapid travel. However, these ideas remain purely theoretical and hinge on principles not yet understood or achievable. Even within the realm of phenomena in nature, things like gravitational waves or shock waves propagate at specific speeds that align with or fall short of light speed limits. While these waves convey information about events like cosmic collisions, they do so within relativistic constraints. As it stands, no established natural phenomenon has been demonstrated to transmit information in a manner that exceeds the speed of light, underscoring the profound implications and constraints imposed by the laws of physics as we currently understand them. The theoretical concept of quantum communication arises from the principles of quantum mechanics, particularly the unique behaviors exhibited by subatomic particles. Unlike classical communication systems, which rely on bits of information that can be in states of 0 or 1, quantum communication takes advantage of quantum bits or qubits. Qubits can exist simultaneously in multiple states, a phenomenon known as superposition. This allows for far greater amounts of information to be processed and transmitted simultaneously. One of the most intriguing aspects of quantum communication is the phenomenon of quantum entanglement. When two particles become entangled, the state of one particle is intrinsically linked to the state of the other, regardless of the distance separating them. If an observer measures the state of one entangled particle, it instantaneously determines the state of its partner. This has led to speculation about the potential for quantum communication to convey information across vast distances, seemingly bypassing the traditional constraints of light speed. To utilize quantum communication effectively, researchers envision a process known as quantum key distribution, which involves the exchange of cryptographic keys between parties through quantum channels. The security of this method arises from the no-cloning theorem of quantum mechanics, which states that it is impossible to create an identical copy of an arbitrary unknown quantum state. This property ensures that any attempt to eavesdrop on the communication will disturb the quantum states being transmitted, alerting the parties involved to the presence of an intruder. For practical implementation across interstellar distances, quantum repeaters may be developed to extend the range of quantum communication. These devices could work by entangling multiple pairs of particles, effectively re-establishing entanglement as the distance between communicating parties increases. While significant challenges remain in realizing a functional quantum communication network over vast distances, ongoing advancements in quantum technology continue to unveil new possibilities, suggesting a future where this cutting-edge concept could enable secure and instantaneous exchanges of information across the cosmos. The idea of cosmic-scale structures functioning as communication networks invites intriguing possibilities within the realms of astrophysics and engineering. Such structures could, in theory, facilitate the transfer of information across vast distances, potentially enabling advanced civilizations to connect with one another or even share knowledge with us. One compelling concept revolves around using natural cosmic phenomena, like pulsars or quasars, as beacons for communication. Pulsars are highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation, which can be detected when the beam is directed toward Earth. Their regular pulsations could provide a reliable and predictable signal structure that advanced civilizations might utilize for long-distance messaging. By encoding information in the timing and frequency of these signals, civilizations could establish a form of communication that traverses the expansive distances between stars. Another fascinating notion involves artificially constructed megastructures, sometimes referred to as Dyson spheres or similar constructs, that harness energy at a cosmic scale. Such structures could theoretically be used to generate powerful signals or to create vast networks of communications using focused laser beams. These constructs would not only enable communication, but could also allow for energy harnessing and management on a scale unimaginable with current technology. Additionally, cosmic strings, hypothetical one-dimensional topological defects in space-time, could also serve as communication conduits if they were to exist. These cosmic structures might possess unique gravitational properties that could influence the propagation of electromagnetic waves. If harnessed properly, these strings could facilitate communication by bending or connecting space in ways that allow for faster-than-light effects, though this remains purely theoretical at this point. The concept of cosmic-scale communication networks speaks to the potential sophistication of advanced civilizations and their ability to manipulate the universe's structures to enhance connectivity. While currently speculative, such ideas stimulate our imagination about the interconnectedness of intelligent life and its capacity to transcend the vast voids between stars. As we explore more about the universe, the prospect of discovering evidence of such networks becomes increasingly captivating. Detecting signals or messages from beyond our observable universe presents a formidable challenge, given that the limits of our current technology and understanding restrict our observations to a finite region of space stretching approximately 13.8 billion years away. However, scientists are exploring several imaginative strategies to uncover potential signals from cosmic sources that may lie beyond this observable horizon. One intriguing approach involves searching for anomalous radio waves or other electromagnetic signals that could come from advanced civilizations. Facilities like the Search for Extraterrestrial Intelligence, or SETI, utilize powerful radio telescopes to scan the skies for anything that deviates from typical cosmic background noise. They would look for narrow bandwidth signals or patterns that suggest deliberate communication rather than random astrophysical phenomena such as pulsars or quasars. This method relies on the premise that advanced civilizations might use similar forms of communication that we can recognize despite the vast distances involved. Another prospective avenue revolves around the study of gravitational waves. These ripples in spacetime, produced by massive celestial events, could potentially carry information from beyond our observable universe. If, theoretically, there exist advanced civilizations engaged in catastrophic astronomical processes, the gravitational waves emanating from such events could carry signatures that might be detectable. This type of information could aid us in understanding the conditions and events occurring far beyond the limits of our current observational capabilities. Additionally, researchers might employ theoretical frameworks within the field of cosmology to detect indirect evidence of events or structures outside our observable universe. This could involve analyzing the cosmic microwave background radiation for signs of gravitational influences or disturbances originating from beyond our detectable horizon. Such methodologies could offer tantalizing clues about events that occurred before inflation set in, leading to the current observable universe. Lastly, theoretical practices in quantum mechanics, such as the proposal of quantum entanglement, might hold potential for future communication mechanisms that exceed our current understanding. Even though concepts akin to faster-than-light communication remain speculative, breakthroughs in quantum communication technologies could someday enable us to explore realms currently deemed unreachable, securing messages from unknown civilizations that might exist beyond the observable universe. Fundamental limits to our knowledge of the universe stem from both inherent physical principles and practical constraints in observational capabilities. One major limitation is related to the speed of light, which acts as a cosmic speed limit according to Einstein's theory of relativity. This constraint means that there are regions of the universe beyond our observable horizon that we can never directly access or receive information from. The finite speed of light restricts us to gathering data only from light that has had enough time to reach us since the beginning of the universe, approximately 13.8 billion years ago. Another significant limit arises from the nature of quantum mechanics. The Heisenberg uncertainty principle, which states that certain pairs of physical properties, like position and momentum, cannot both be precisely measured at the same time, imposes constraints on our ability to have complete knowledge of a particle's state. This principle hints at a fundamental limit to our ability to predict the behavior of particles and systems, leading to inherent uncertainties that permeate the fabric of reality. Additionally, the complexity of the universe presents challenges in our understanding. The interactions of the fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, create systems that can be incredibly intricate. From black holes to complex biological systems, the emergent properties that arise from these interactions often defy straightforward explanations or predictions. As we delve deeper into these complex systems, we confront computational limits in modeling and simulating their behavior accurately. Lastly, the philosophical implications of our knowledge also play a role in defining limits to our understanding. Questions about the multiverse or the nature of reality itself may forever remain beyond our grasp, transcending empirical investigation. The quest for a unified theory that encompasses all the fundamental forces remains an ongoing challenge, and it is possible that certain aspects of existence may exist outside our capacity to measure or comprehend. These various limitations collectively shape the boundaries of human knowledge, guiding our pursuit of understanding while continuously revealing the vast mysteries that still await discovery. Our observational tools and methods play a crucial role in shaping our understanding of the cosmos, and they come with inherent limitations that can restrict our knowledge. One major limitation stems from the wavelengths of light and other electromagnetic radiation that we are capable of detecting. Classical telescopes primarily observe visible light, restricting our view to a narrow slice of the electromagnetic spectrum. While advancements in technology have enabled observations across infrared, ultraviolet, radio, and gamma-ray wavelengths, each spectrum presents challenges. For example, atmospheric interference affects ground-based observations, while satellite-based instruments can only observe from certain altitudes, limiting access to specific parts of the sky. Another significant limitation arises from the resolution of our instruments. Although technologies like adaptive optics have enhanced the clarity of ground-based observations, there are still fundamental constraints related to diffraction limits. This phenomenon restricts the ability of telescopes to resolve closely spaced objects or faint sources of light. As a result, we may miss out on important details about distant celestial phenomena, such as the formation of galaxies or the dynamics of exoplanet systems, due to the constraints of our imaging capabilities. The timescales involved in cosmic events also impose limitations. Some astronomical phenomena, such as supernovae or the merging of black holes, occur over spans of time that exceed typical human observational efforts. Our understanding of transient events relies heavily on timely detection and monitoring, but the vast distances involved can mean that we observe these occurrences only after a significant time delay. This influences our ability to study their full life cycles and understand their underlying mechanisms. Additionally, our reliance on theoretical frameworks to interpret observations introduces a layer of uncertainty. These models, while robust in many aspects, are often based on simplifications and assumptions that may not account for the full complexity of the universe. As we gather more data, it sometimes challenges existing frameworks, leading to revised understandings that highlight previous shortcomings. The interplay between observation and theory continually shapes our grasp of the cosmos, illustrating that while our tools enable remarkable discoveries, they also impose barriers that guide how we interpret and understand the magnificent universe around us. Several significant gaps exist in our current models of the universe, presenting challenges to our understanding of cosmology and fundamental physics. One of the most profound gaps involves the nature of dark matter and dark energy. While observations suggest that dark matter constitutes approximately 27% of the universe and dark energy comprises roughly 70%, their exact properties remain largely elusive. We know dark matter interacts through gravity but does not emit or absorb light, making it difficult to study directly. Similarly, dark energy is theorized to be responsible for the accelerated expansion of the universe, yet little is understood about its origin or fundamental nature. Another key gap is our incomplete understanding of how gravity interacts with quantum mechanics. Currently, general relativity describes gravity on a cosmic scale, while quantum mechanics governs subatomic particles. However, reconciling these two frameworks into a single coherent theory, often called quantum gravity, remains one of the most significant challenges in modern physics. Attempts to formulate a complete theory have led to various candidates, such as string theory and loop quantum gravity, but no consensus has yet emerged, leaving the fundamental aspects of spacetime and gravity shrouded in mystery. Additionally, the origins and nature of the universe itself pose significant questions. While the Big Bang theory provides a robust framework for understanding the universe's evolution, it leaves certain critical aspects unexplained, particularly what happened during the very earliest moments of existence, or what might have preceded the Big Bang. Concepts such as inflation attempt to address these issues, but the specifics of these processes and the underlying mechanisms remain speculative. Finally, our models often struggle to account for the emergence of complexity and life within the universe. Despite robust frameworks for understanding the chemical processes that may lead to life, the precise conditions necessary for life to arise in various environments are still poorly understood. This gap extends to how life could exist in extremes or on exoplanets, further complicating our understanding of the universe as a dynamic and diverse system. Together, these gaps illustrate that while our current models provide valuable insights, they also highlight the need for ongoing inquiry and exploration in the quest for a deeper understanding of the cosmos. Future technologies hold immense potential to expand our ability to observe and understand the universe in ways that current instrumentation cannot. One significant advancement lies in the development of more powerful and sensitive telescopes. Next-generation space telescopes, such as the James Webb Space Telescope, aim to capture infrared light from distant celestial objects, allowing us to study the formation of stars and galaxies in unprecedented detail. Further advancements may include telescopes capable of observing other wavelengths, such as gravitational waves, enabling us to explore new aspects of cosmic events like black hole collisions. Additionally, the construction of large-scale observatories on Earth and in space will enhance our observational capabilities. Imagine arrays of radio telescopes working together in a coordinated fashion, like the Very Large Array, but expanded on a planetary or even interplanetary scale. This type of technology could improve resolution and provide a clearer picture of cosmic phenomena, allowing us to peer deeper into the mysteries of the universe. Data analysis methods will also undergo a transformation with the advent of artificial intelligence and machine learning. These technologies can process and analyze the vast amounts of data generated by modern observational instruments, identifying patterns and anomalies much more swiftly than human researchers. As telescopes capture more data, advanced algorithms could help detect transient events or classify celestial objects, offering new insights and enhancing our understanding of cosmic phenomena. Moreover, the integration of quantum technologies may revolutionize our observational techniques. Quantum sensors could achieve precision measurements of gravitational waves and other subtle phenomena that are currently challenging to detect. This could unlock new ways to study the universe, providing insights into both general relativity and quantum mechanics, possibly leading to breakthroughs in how we understand the fundamental forces of nature. Through enhanced telescopic capabilities, advanced data analysis, and the integration of emerging technologies, our ability to observe and interpret the universe will expand dramatically. These advancements will not only deepen our understanding of celestial mechanics, but also potentially reveal new phenomena that challenge or refine existing scientific theories, driving the exploration of the cosmos into exciting new territories. Certain questions about the universe may remain fundamentally unanswerable, posing challenges that lie at the intersection of science, philosophy, and the limits of human understanding. One of the most profound inquiries revolves around the nature of the universe's origin. While theories such as the Big Bang provide a framework for understanding the universe's evolution, the question of what preceded it, or even what caused it, delves into realms that may escape empirical investigation. The nature of time itself, and whether it existed before the Big Bang, are areas shrouded in uncertainty, making definitive answers elusive. Another crucial area explores the fundamental nature of reality. Questions like, what is the ultimate purpose of the universe? Or, is there a meaning behind existence? Venture into philosophical territory. While science can provide descriptions and predictions about how the universe functions, it might not hold the keys to answering existential queries that pertain to purpose or meaning. Such inquiries reflect the limits of scientific inquiry when addressing the subjective experiences and interpretations of consciousness. The concept of the multiverse also raises questions that may be fundamentally unanswerable. If our universe is just one among many, each with potentially different physical laws and constants, it poses challenges in terms of obtaining evidence. The very nature of a multiverse may make it impossible to observe or interact with other universes, limiting our understanding of their existence. This non-falsifiability raises profound questions about the nature of scientific theories and their ability to be tested and validated. Finally, inquiries into the true nature of consciousness could present fundamental challenges. While neuroscience and psychology continue to unravel the complexities of the human mind, questions like, what is consciousness? Or, how does subjective experience arise from neural processes? May venture beyond the realms of empirical science. The intricate relationship between consciousness and the universe might end up eluding definitive explanations, representing a blend of science and philosophy that remains largely mysterious. Together, these questions highlight the boundaries of our current scientific framework and the philosophical dimensions that accompany our quest for knowledge about the universe. While science consistently seeks to expand our understanding of reality, it may confront questions that inherently resist conclusive answers, emphasizing the depth and complexity of existence. The concept of a cosmic string arises from theoretical physics, particularly in the context of field theory and cosmology. Cosmic strings are hypothetical one-dimensional topological defects that could form during phase transitions in the early universe, similar to how a crack might form in the ice of a frozen lake as it cools. They are envisioned as incredibly thin, yet extremely dense objects that may stretch across vast distances in space, potentially encompassing massive amounts of mass and energy along their lengths. These strings would possess remarkable properties due to their unique structure. Cosmic strings could exert gravitational forces strong enough to influence the surrounding space-time, leading to fascinating and potentially observable phenomena. For instance, the gravitational pull of a cosmic string might cause space to warp around it, creating effects that could be detectable by future observational instruments. This distortion might result in gravitational lenses that magnify and stretch light from distant galaxies, providing a method to search for evidence of their existence. In addition to their gravitational effects, cosmic strings could play a role in the formation of cosmic structures. As the universe expands and evolves, cosmic strings might act as seeds for galaxy formation and large-scale structures, guiding matter into specific regions and influencing the distribution of galaxies. Their presence in the early universe could lead to varied patterns in the cosmic microwave background radiation that we observe today, offering a potential signature for their historical impact on cosmic evolution. Moreover, cosmic strings could be tied to high-energy physics and help bridge the gap between quantum mechanics and general relativity. They may provoke important insights into fundamental forces and the conditions of the early universe, particularly during periods of rapid expansion known as inflation. While the existence of cosmic strings remains speculative, their study encourages exploration into the nature of the universe's fabric and promotes discussions about the fundamental building blocks of reality itself. As our understanding deepens, the implications of such cosmic anomalies may unveil new dimensions of the cosmos we have yet to comprehend. The concept of a false vacuum refers to a metastable state in quantum field theory, where the vacuum energy is higher than the true vacuum energy. In this context, a false vacuum appears to be stable and does not spontaneously decay into a lower energy state, even though it is not the most energetically favorable configuration. The existence of stable regions of false vacuum in the universe raises intriguing possibilities regarding cosmology and the dynamics of the cosmos. If stable regions of false vacuum exist, they could have profound implications for our understanding of the universe's structure and evolution. For instance, a false vacuum could influence the behavior of fundamental forces, altering the properties of space-time and the interactions between particles. Such regions might give rise to unique physical conditions that differ significantly from those found in our observable universe, potentially supporting exotic states of matter or new forms of energy. One of the most striking implications of a false vacuum is the possibility of initiating a phase transition. If a region of false vacuum were to decay into a true vacuum state, it could trigger a bubble of low-energy vacuum to expand rapidly, leading to a phenomenon known as vacuum decay. This process could release immense amounts of energy and could manifest as a catastrophic event, transforming the surrounding regions of space and fundamentally altering the fabric of reality. Such transitions might have been responsible for the dynamics of the early universe, including the rapid expansion associated with inflation. Additionally, the study of false vacuum scenarios invites exploration into the concept of cosmic landscapes, where multiple vacuum states coexist within the universe. This framework suggests the universe might have a complex structure of vacuum states, each with distinct physical properties and implications for the formation of matter, forces, and even the emergence of life. While the existence of stable regions of false vacuum remains a theoretical proposition, continuing research into quantum field theory and cosmology may shed light on their potential presence. If such states were to be confirmed, they would deepen our understanding of the nature of the universe and its underlying mechanisms, opening new avenues for investigating the fundamental physics that govern reality. Cosmic domain walls are hypothetical two-dimensional topological defects that could form during phase transitions in the early universe, similar to how domain walls in magnetism arise when regions of differing magnetic orientation create boundaries. In the context of cosmology, cosmic domain walls occur when a scalar field undergoes a symmetry-breaking phase transition, leading to the formation of distinct regions, each with different vacuum states. These walls represent boundaries between regions of space that have settled into different vacua, essentially different states of energy and physical properties. The existence of cosmic domain walls suggests that the universe might be structured with a complex interplay of vacuum states, potentially impacting the way matter and energy are distributed. During the early moments of the universe, as it cooled, fluctuations might have caused regions to adopt different vacuum configurations, resulting in the creation of domain walls separating these regions. One key aspect of cosmic domain walls is their stability. Depending on the dynamics of the scalar field responsible for their formation, these walls could be stable, unstable, or transient. Stable domain walls, if they exist, would persist over cosmic timescales and could influence the evolution of the universe. They might act as barriers that could trap certain types of particles or energy, influencing the distribution of matter and radiation, and potentially impacting the formation of large-scale structures like galaxies. The formation and stability of cosmic domain walls raise significant questions about their implications for cosmic evolution and matter distribution. If such walls exist, they could leave observable signatures in the cosmic microwave background radiation or affect the dynamics of gravitational collapse, leading to galaxies and clusters of galaxies. While the existence of cosmic domain walls remains theoretical, their study provides insight into the behavior of the universe during its formative stages and promotes further exploration of the complex mechanics underlying its structure. Understanding these defects can enhance our grasp of the fundamental principles that govern the cosmos and influence the conditions necessary for the emergence of complex structures, including life. The idea that entire universes could exist within the event horizons of black holes is an intriguing concept related to theoretical physics and cosmology. This notion is often discussed in the context of black hole thermodynamics and the information paradox, which grapple with the fundamental nature of space, time, and information within black holes. When a black hole forms, it creates an event horizon, which is a boundary beyond which nothing can escape, not even light. At this boundary, the laws of physics as we know them begin to behave in unfamiliar ways. Some theories propose that the interior of a black hole might be linked to other regions of space-time, potentially leading to the idea that a black hole could serve as a portal to another universe. This connection could arise from the geometry of space-time and the relationships between gravity and quantum mechanics. One concept related to this hypothesis is the idea of a wormhole, which theoretically could connect two separate points in space-time, possibly leading to other universes. If a black hole acts like an entrance to a wormhole, the interior of the black hole may harbor a separate universe with its own physical laws. This idea suggests that what we perceive as a black hole could be a doorway to a different realm of existence, potentially containing its own galaxies, stars, and even life. Moreover, the notion of universes within black holes connects to the concept of cosmic inflation, where the rapid expansion of the universe after the Big Bang could produce regions of bubble-like spaces, each evolving into distinct universes with unique properties. If black holes indeed harbor such regions, they might contribute to a multiverse scenario, where each black hole contains its own self-contained universe. While these ideas are fascinating and invite contemplation about the nature of reality, it is important to note that they remain largely speculative. Current understanding of physics does not provide robust empirical evidence to confirm the existence of entire universes within black holes. However, as research in quantum gravity and black hole thermodynamics advances, we may gain new insights into these enigmatic objects and the profound mysteries they embody in the fabric of the cosmos. The fuzzball theory of black holes is a concept derived from string theory that seeks to resolve paradoxes associated with black holes, particularly the information paradox. Traditionally, black holes are thought to be singularities surrounded by event horizons, where the laws of physics break down and any information that falls into them appears to be lost forever. However, the fuzzball theory challenges this classical view by proposing that black holes are not empty regions of spacetime, but rather highly complex structures composed of strings and branes. According to the fuzzball theory, a black hole can be visualized as a fuzzball, which is essentially a collection of strings and other fundamental objects in a tangled state, filling the region that we would typically attribute to a black hole. This model suggests that instead of having a singularity at their core, black holes are characterized by a distribution of energy and information. The structure of the fuzzball encapsulates the black hole's mass and charge, and its unique characteristics might prevent the loss of information, allowing it to be preserved rather than annihilated. One significant implication of the fuzzball theory is its impact on our understanding of spacetime. In this model, the fuzzball's surface represents a kind of effective horizon that can replace the traditional event horizon of a black hole. The dense nature of the fuzzball allows for quantum effects to play a critical role, suggesting that spacetime itself may not behave in the classical sense we typically envision. Instead, it hints at a more granular or networked structure that is influenced by the underlying fundamental components described by string theory. Additionally, the fuzzball theory aligns with the holographic principle, which posits that the information contained within a volume of space can be represented as a theory on its boundary. This principle implies a profound relationship between gravity, quantum mechanics, and information, suggesting that our understanding of the universe is interconnected in ways that challenge conventional notions of spacetime. Though the fuzzball theory provides a compelling alternative to traditional black hole models, it remains a theoretical framework that requires further development and validation. As research in string theory and quantum gravity advances, this perspective may deepen our understanding of black holes and the fabric of spacetime, potentially unlocking new realms of knowledge about the universe and its fundamental nature. The anthropic principle is a concept that explores the relationship between the universe's physical laws and the existence of conscious observers within it. Essentially, it asserts that the universe must have properties suitable for life, specifically human life, because we are here to observe it. The principle can be framed in two main forms: the weak anthropic principle, which states that the observed values of the universe's physical constants must allow for the existence of observers, and the strong anthropic principle, which suggests that the universe's properties are in some way compelled to support life. This principle has significant implications when examining the apparent fine-tuning of our universe. Many fundamental constants, such as the gravitational constant, the strength of electromagnetic forces, and the masses of elementary particles, seem to be precisely calibrated to allow for the emergence of stars, planets, and ultimately life. If these constants were even slightly different, the universe might be dramatically less hospitable or entirely hostile to life. For instance, if the strong nuclear force were weaker, atomic nuclei could not hold together, preventing hydrogen and helium from forming the stars necessary for complex chemistry. The anthropic principle posits that we can only observe these finely tuned conditions because we exist in a universe where they happen to prevail. This leads to the notion that our universe is one of potentially many universes, or a multiverse, each with different physical constants and laws. In a vast multiverse, the anthropic principle provides a framework for understanding why we find ourselves in a universe that appears perfectly adjusted for life. We happen to be in one of the rare instances where the conditions are suitable. Critics of the anthropic principle, however, argue that it may not provide a satisfactory explanation or justification for fine-tuning. Some indicate that it lacks predictive power and does not address why these constants have the values they do in the first place. Instead, they advocate for theories that could demonstrate why our universe's specific properties emerged from the underlying physics. Ultimately, the anthropic principle serves as a thought-provoking lens through which to explore the relationship between human existence and the universe's fundamental characteristics, provoking deeper inquiries into why our cosmos is structured in a manner that allows for life as we know it. The possibility that fundamental constants of our universe could differ in regions beyond our observable horizon is a subject of considerable speculation in theoretical physics and cosmology. Fundamental constants, such as the speed of light, gravitational constant, and the charge of an electron, are pivotal in shaping the physical laws that govern the universe. If these constants were not uniform throughout all of spacetime, it might open the door to a variety of cosmic phenomena and different physical realities. Within the framework of certain cosmological models, particularly those involving the concept of a multiverse, it is suggested that there could be regions of the universe where distinct physical laws and constants apply. In this multiverse scenario, each universe might emerge from different quantum fluctuation mechanisms, resulting in unique combinations of constants. For example, one universe might have a stronger gravitational force, while another might feature different properties of fundamental particles. This diversity could lead to varied outcomes regarding the formation of structures such as galaxies, stars, and potentially even life. Moreover, theories such as string theory propose that additional dimensions exist beyond our observable three-dimensional space. The geometry and configuration of these extra dimensions could contribute to varying physical constants within different regions of the cosmos. As matter and energy interact with these dimensions, the resulting effects may produce universes with distinct physical realities. Investigating the implications of differing fundamental constants also raises fascinating questions about the nature of existence. Regions with alternate constants might not only influence the structure of matter, but could also affect the emergence of complexity and life itself. In universes where the forces are significantly altered, the pathways for chemical reactions and stability of atomic structures might diverge dramatically from what we observe, potentially yielding entirely different forms of existence. While current empirical evidence does not confirm variations in fundamental constants beyond our observable universe, the exploration of such ideas encourages deeper reflection on the nature of reality and the profound mysteries that continue to challenge our understanding of the cosmos. As advancements in cosmology and theoretical physics unfold, we may gain further insight into the possibilities that lie beyond the limits of our current observation. The multiverse concept provides a compelling framework for understanding the apparent fine-tuning of our universe by suggesting that our universe is just one of many, each with its own distinct set of physical constants and laws. This idea emerges from various theoretical interpretations, particularly within cosmology and string theory, which suggest that multiple universes could be created through different mechanisms, such as cosmic inflation or quantum fluctuations. In a multiverse scenario, the fundamental constants that govern physical laws are not fixed, but can vary across different universes. This implies that while our universe appears finely tuned for the existence of life, such as possessing the right gravitational strength, electromagnetic force, and balance of fundamental particles, other universes could have entirely different properties. In fact, most of these universes might not be conducive to life as we know it. The multiverse concept posits that among the vast multitude of universes, it is not surprising that at least one universe like ours would have conditions suitable for life. This framework provides a natural explanation for the fine-tuning problem. Instead of requiring a singular explanation for why our universe's constants have the specific values they do, the multiverse suggests that we simply inhabit a universe where those particular conditions happen to occur. If there are countless universes constantly being generated in an eternally expanding multiverse, the likelihood of one with the right combination of constants increases significantly. Consequently, the fine-tuning of our universe could be seen as a selection effect. We observe it because we are here to observe it. However, this multiverse interpretation is not without its controversies and challenges. Critics point out that the multiverse concept may lack empirical testability, as distinguishing between unobservable universes is inherently difficult. Furthermore, it raises questions about the underlying mechanisms that lead to the diversity of fundamental constants and the implications of these differences for the nature of reality itself. As research in cosmology and theoretical physics progresses, the multiverse concept continues to offer fascinating insights into the nature of existence and the underlying principles that shape our universe. While the discussion remains largely theoretical, the exploration of these ideas invites deeper reflection on the profound mysteries surrounding the fabric of the cosmos. If fundamental constants were slightly different from their observed values, the implications for the universe could be profound and far-reaching. These constants, such as the gravitational constant, the speed of light, and the strengths of the forces governing atomic interactions, play critical roles in shaping the fundamental behavior of matter and energy. Even small deviations from their current values could lead to dramatically different physical realities. For instance, consider a scenario where the gravitational constant was slightly stronger. In such a case, gravitational forces would be more effective at pulling matter together. This might lead to stars becoming larger and burning out more quickly due to increased gravitational pressure. The enhanced gravity could also affect the formation of planets. They might become denser, potentially leading to a universe filled with more massive, short-lived stars and possibly fewer habitable planets, as the conditions for stable orbits would change dramatically. Conversely, if the gravitational constant were weaker, the effects would be equally significant but lead to different outcomes. Under a weaker gravitational influence, stars could struggle to maintain the nuclear fusion processes necessary for their stability, leading to a universe populated by smaller, cooler stars. Additionally, galaxies might form differently or not at all, drastically altering the large-scale structure of the universe and raising questions about the potential for complex structures, including life. Similarly, altering the strength of electromagnetic forces would have tremendous implications. If this force were slightly stronger, the interactions between electrons and nuclei would become more pronounced, potentially resulting in a universe where atoms are too tightly bound to allow for a diverse array of chemical reactions. Conversely, if electromagnetic forces were weaker, atoms might not hold together effectively, preventing the formation of complex molecules necessary for life as we know it. Other fundamental constants, such as the masses of elementary particles, also play critical roles in determining the behavior of matter. Variations in these values could change the stability of atomic nuclei, leading to a universe where the processes of nucleosynthesis, the creation of new atomic nuclei in stars, might be significantly altered or even impossible, affecting the abundance of elements that are essential for chemical complexity. In sum, if fundamental constants were slightly different, the universe could exhibit drastically altered properties that may hinder the formation of galaxies, stars, and planets, ultimately influencing the potential for life. These hypothetical scenarios underscore the delicate balance that characterizes our current universe, where even minimal changes in these constants could lead to a reality fundamentally different from the one we inhabit. The idea that there could be universes with completely different fundamental laws, yet still support complex structures, or life raises fascinating possibilities in the realm of theoretical physics and cosmology. While our own universe operates under a specific set of physical laws and constants that promote the emergence of life as we understand it, the exploration of alternative laws invites speculation about what forms of complexity or even life could exist under entirely different conditions. In theory, if the fundamental forces such as gravity, electromagnetism, and the strong and weak nuclear forces were drastically altered, it might still be possible to form complex structures. For instance, if gravitational attraction was significantly weaker, it might still allow for the formation of planets, but the dynamics of star formation could be radically different. Stars might be less massive and more numerous, potentially giving rise to unique stellar environments that could foster different types of chemical reactions and structures. Similarly, if the constants governing atomic interactions or particle masses were altered, it could lead to alternative forms of chemistry that do not rely on carbon-based life as we know it. For example, if silicon or another element could serve as a foundation for complex molecules, entirely different biochemical systems might emerge. There are even hypotheses regarding the possibilities of life forms existing in extreme conditions or under different energy configurations, such as life based on ammonia instead of water, which could theoretically operate under different physical laws. Speculative scenarios sometimes involve the existence of universes described by different mathematical frameworks entirely, allowing for life to emerge within the bounds of those new laws. Some scientists theorize that there could exist complex structures governed by quasi-physical rules that simulate life in ways that are not confined to our current understanding of biology or chemistry. For instance, structures could arise that are similar to life, but based on different principles of organization and interaction. However, the challenge in discussing universes with vastly different fundamental laws lies in our limited ability to predict and comprehend such arrangements. The very essence of life as we know it is intricately tied to the specific conditions and constants that shape our universe, making it difficult to envision how different laws could yield forms of life that we might recognize or understand. While the notion is highly theoretical, exploring the possibility of such universes encourages deeper philosophical and scientific inquiry, reminding us that the universe might harbor a diversity of life forms and structures that extend beyond our current understanding, awaiting discovery in realms we have yet to explore.